No audio.
Welcome to the Onethinx LoRaWAN workshop, everyone. Can you hear us? Can you just confirm in the comments, please? That's perfect.
Okay, great.
Cool.
Hello, everyone, again. Thank you, everyone, for joining today, and especially thanks to our speakers. We are very excited to have you all here. We will start with the first part of our presentations of our speakers, IoT experts, and later on, from 7 p.m. set time zone, we will also welcome you to our hands-on workshop, which will be led by our colleague Tomislav Berlek. Now, let me first introduce our speakers. Alcho Medema, lecturer and researcher from University of Applied Sciences in the Netherlands. Dario Buma, product manager at Lecuna Space. Then we have Srikant Nirela, senior product manager from Infineon, and Ruth Kerstens, CEO of Computronics. And then we have our CTO of Onethinx, Rolf Noteboom, and Tomislav Berlek, application engineer from Onethinx. Welcome, everyone.
Thank you. Thank you, Anita.
Shall we start with the first presentation of Alcho in smart farming?
Sure.
Alcho, the word is yours.
Thank you very much, Anita. Let me share my screen. So here I am. If all is okay, you can now see the blue screen with green things. And I'm going to tell you about agricultural use precision farming for sensors. This is me. I'm working at Eres University, but I'm at the same time developing, together with my partner, sensors for green things. I'll come later to the name. It's not a coincidence that it looks like Onethinx. Our aim is to provide data enhanced with solid agronomical background to support better decisions, because farmers, they have lots of challenges. There's lots of challenges. We show some tools and opportunities, and the why, one of the reasons why. Agriculture is expanding, more and more data is coming, farmers are getting larger, labor is getting less, so more acres per person, more hectares per person, and if you cannot measure it, you cannot manage it. That's why you need good data, and we want to help farmers provide good data.
Your presentation is off, so we will try to tune in ASAP. In the meantime, I would just like to involve my colleague Tomislav regarding smart farming.
No, Alcho has to open the presentation.
Yes, we will also open the presentation. Just a moment.
No. Alcho has a presentation. Alcho needs to share it. Probably.
Yeah, it's not shared yet, Alcho.
It's not share, but I clicked on share. Why is it not shared? How come it is not shared? I click on share, I'll click again on share screen. Unable to share screen. What is this now? I'm doing the same as yesterday.
Would you like to join? Give us a few moments, please.
What the? I don't know what's happening. I'm not able to share. I'm doing exactly the same as yesterday. It doesn't allow me to share. I don't have permissions to share. Somehow it has nothing different than yesterday. Oh, that's nice. That's my ceiling. How come you're seeing my ceiling? Where is that from? It's because it's using...
To present our colleague Tom, who will also tell you more about our kit for smart farming. Hello, Tom.
Hey, hello everyone. So as Anita already mentioned, my name is Thomas LoRaWAN. I will do the workshop today on smart farming with Onethinx module, or an introduction even to beginners, but also to more professional people, or to get into farming with Onethinx module. And today we will be using this amazing dev kit developed by Onethinx that measures soil temperature, soil humidity, air temperature, and light. And it's all contained here on this small board. It has a Onethinx module on it. You can go on our GitHub page to follow the instructions. If you have this Sprouty here, you can get workshop introduction on our GitHub, and there you see how to set everything up to use with Sprouty, and so you can follow along today on the workshop. Yes, and it has the Onethinx module on it. And it has some amazing capabilities. With this integrated antenna, we are able to get kilometers and kilometers of range. That is right, Christian. It's the code is open source for Sprouty, and the end version is not out yet, because we have to go to the workshop and then release the end version of the code. But you can stay, even if you don't have Sprouty, you can stay and follow along and see how easy it is to use Onethinx module. Actually, this blinking LED that you see here is blinking not through code, but through an FPGA-like structure that's located inside the PSoC chip. So there are things that can be run without actually writing code, and this is just one of the things that's interesting there. And later you will see us in the workshop, and we can go through it together. If you do not have a Sprouty, you can still order it right now. It will, of course, not come in time for this workshop, but you can test it later yourself. We can see Alcio now.
I'll give it another try.
Maybe a few more minutes. Guys, maybe it's an idea to get some good coffee. We have some good coffee here at Onethinx. We have dedicated people for that, and last time I was so well caffeinated I couldn't sleep. So yeah, maybe they don't want me to sleep again. So yeah, get your coffee. Even it's good to have a glass of water beside you, so if you're testing Sprouty out, that you can actually put it in water, so so you see the moisture change. Christian, you're correct. That's the introduction. If you have Sprouty, that's the introduction how to set the environment up using Visual Studio Code and PSoC Creator. And then if you go just to Sprouty workshop without the introduction, then there you can see steps we will have during the workshop to guide you through. That's about it about our powerful Sprouty here. Yeah, and it has amazing capabilities. Onethinx module is used in projects around the world, heavily in Italy in agriculture, but also in Netherlands, in US, and everywhere around. Okay, we see something now.
Yes, there are some changes. We are very sorry for some technical problems, but here we are with Alcio, and very excited to hear from his vision on smart farming. We can see your screen now.
Yes, you can see
Alcio?
me, you can hear me, I suppose as well. Oh, I hear lots of echoes. So yes, well, I hope you heard before. I just switched browser, switched off my phone, and now everything is normal. Don't know why it was like that, but doesn't matter. We are here now. So as I explained, I hope you heard that we started GreenThinx in 2020 together with a partner of mine, Cor Haanstra, and our aim is to provide data enhanced with solid agronomical background to support farmers with making better decisions. Because agriculture today has many challenges, and one of the challenges is that there are more acres, more production per person, so there is more that you need to manage, and for managing well, you need good data. So if you cannot measure it, then you cannot manage it. And that's what we want to assist farmers with. Part of this is, well, as we look around us, we see soil and we see climate, and soil and climate for a farmer, the combination of soil and climate means yield. We have an actual yield, we have a feasible yield, and we have a potential yield. And all of this is influenced by the condition of the soil and by the acts of climate, like we are looking now around us in the northern part of Europe. It's very wet, so climate is really disturbing agricultural practices. At this moment, we don't need to do any measuring of soil moisture. It is really wet. But in normal circumstances, still, soil is very important. So the texture, what kind of soil does a farmer have, but also the quality, chemicals, and then chemicals as in nutrients, and biological, of course, soil life. And on this, the farmer has a small impact, but farming itself is a huge impact. And farming itself, last year we had a wet harvesting season, so at that time it's very difficult to keep your soil in a good condition. And because we are having a very wet spring this year, you can still see the bad condition of the harvest last year. Because of tracks, because of compaction, the water cannot leave the soil, the water is on the soil. So that's a huge impact of farming. And in this, water is very crucial. That's very obvious in this spring as well. And the climate is getting more and more unpredictable, more extremes. Like I said, we had a very wet harvest season last year, and we're having a very wet spring this year. But in the previous years, we had very hot summers, and that's all over the globe. The rhythm of heat waves and rainfall are changing. And that requires a shift in management. You need to apply your inputs only when needed. For example, your nutrients. If you apply all your nutrients at the start of season and you have a very wet season, then you have a high risk of losing these nutrients. And that's what you don't want. You need to act, or as good as possible, to act on soil and crop data if available. Well, that's how we want to assist the farmer with providing good soil data. Because this is a graph with lots of information, and the most important part is the water and nutrients, which is almost in the center of the graphic. Because once planted, water and nutrients is the only way that a farmer has an effect on the outcome of the crop. And the effect of applying water and nutrients depends very much on the condition of the crop and on the condition of the soil. So that's stuff we want to discuss with the farmer beforehand. That's what we are doing at university as well, to assist in getting this in the best possible condition. And still then you need to have good data for the right timing to apply your water and possibly your nutrients as well. Then what is water in the soil? Because that's what we want to show, that's what we want to measure. Well, water in the soil is presented by the water retention curve, the PF curve, and that's a scale where you can see different lines here for clay, soil, sand and loam. And you see these lines starting and ending at different points on the X and Y graph axis, which means that different soils have different capacities of holding water. So a sandy soil can hold only little water, a clay soil can hold much more. And that's what we use as input, this information for the sensor to provide good data. Just to make it more graphic, what we have now here in many parts of Holland is on the right side. The soil is saturated, and a saturated soil means that there is hardly any or none air in the soil, and this causes the roots and soil life to suffocate. So your soil is getting worse in condition, and your plants are suffering to survive. In the normal circumstances, normal ideal situation, you would have the center situation where you have water, solid particles and air in your soil, because your roots need air, your soil life needs air. And then on the left you see hygroscopic water. In especially clay soil, loamy soils, there is still a lot of water left in the soil which is not plant available, because it's bound by the soil particles too hard to be released by the suction of the plants. Well, a soil is to a crop as a battery. So the higher capacity of the soil, the better potential yield you can get. And then in this, a clay soil on the left-hand side has a higher capacity than a sandy soil. So it can not only store more water, it can also store more nutrients. Then still we are trying not to irrigate too much, of course. So can we depend on water that's coming from groundwater level? Well, in this case, you can see that from groundwater level upwards on a clay soil, you might have 2.5 meters of capillary rise. So if your groundwater table is between 2 and 2.5 meters, it's still possible for plants to receive this water. On a sandy soil, this can be only 15 centimeters, so that's very shallow. And this capillary rise is not many millimeters, so it's not for the maximum growth, but it's for survival of the plants. And this is showing you why it's only survival. Any plant has its water uptake for 70%, depending on the first 50% of its root depth. Root depth meaning the depth in which the roots will penetrate your soil, your topsoil, where you have all your nutrients. And this can be wheat, this can be onions, this can be rice, this accounts for all crops. Then still we don't want to irrigate, we want to use our rain as effective as possible. Well, we are losing water from rain because of runoff. You are maybe on a slope, so you will have runoff. If your soil is saturated and you don't have a compacted layer, it will hopefully go down to deeper layers, so deep percolation. You will have some evaporation at the same time as your rainfall, and the rest can be hopefully buffered in your root zone. Well, the problem that we have now, we have lots of rain, so we have lots of deep percolation, as we call it. So it's water that goes below the root zone. And it's unfortunately not only water going this deep, this water is taking nutrients as well. Plants are still small, plants can even be bigger, but this water is not just water going down, it's also nutrients going down. And these nutrients then leach outside of the root zone, and they're leaching into the environment. That's also something we don't want. Well, types of irrigation. And now that we have done everything in our capacity to maximize the buffer, we still don't have enough water, so we need some type of irrigation. Well, there's many types. The oldest one is on the top is flood irrigation. It's a proven technique, works, no problem. But there's a high risk of over irrigation and thus anaerobic circumstances because you're pushing out all the air out of the soil. Sprinklers, very widely used, fixed capacity, a lot of work to place them and to take them out, but very straightforward. The moving gun and the moving boom, used a lot in Europe, outside of Europe as well. Wind sensitive, high capacity for the moving gun, less wind sensitive for the moving boom, but the moving boom traveling at the same rate with the same rate of water is giving a lot of water per minute, so high intensity is more expensive. Then in the US, but also in Arabia, you see many pivots. You see them in South America, you see them in China, in Australia, everywhere. Fixed location, fixed capacity, fertigation possible. And fertigation is adding nutrients to the water. And the last one, drip lines, and that's the one we are also focusing on. Drip lines is hoses that you put in the soil where you have a very high efficiency because there's no evaporation straight from your irrigation. Fertigation is possible. It's very solid control, and it can also be used under more saline conditions. So if your water quality is not very super, it's very dangerous to irrigate from the top. You might have some salts in the water which will burn the crop. You can still use this water under drip conditions. So then our solution, what are we putting together? Well, we have sensors, and this is a single cell shown, and I don't know if my camera is on, but you should be able to see the sensor that I'm holding. So this cell is in the tube, each 10 centimeters, and they measure soil temperature and soil moisture. Each 10 centimeters, and you can stack them. They will give a fast response to the pole when it's asked for data, and it's got a low power usage. Now, this is no surprise. We use Onethinx for communication. We are already talking with Onethinx since 2020. And that's how we also came to the name of GreenThinx, because Onethinx was there doing their one thing, which is communication. And we want to make things all green. So that's why we are GreenThinx. On Onethinx, of course, we are using the LoRaWAN for the communication. We're also using the Bluetooth for configuration. For example, if we want to update the firmware, etc. Well, together with the Onethinx and our sensor boards, this is the sensor. It's a tube filled with casting. It's a sensitive sensor for water, but it cannot get wet. Temperature range -20 +65. Two batteries in it, and it can work for at least 2 years on this battery. Next on our wish list might be a solar panel to be able to keep it in the field as long as we desire. And what does it do, this sensor of ours? Well, it communicates every 15 minutes. That's how we set it. We can change this interval, of course, but for now we're doing this every 15 minutes, and then we aggregate this into our hourly data. It collects soil moisture and soil temperature data per 10 centimeters of the root zone of depth that we are measuring. We're going to visualize this in an app, of course, have an API to connect to other platforms, to connect to actuators, and to combine even with weather and other data to have the best predictions for your irrigation advice. So targeted uses, of course, farming. Any crop it can operate in. Of course, you want the high yielding crop financially because they are not for free, unfortunately. So it's those crops that are crucial, depending on water, with a high outturn in money-wise as well. And last but not least, or very important, also those crops where we can have the precision irrigation and fertigation, so where we are using the drip lines. And those crops, they can be the standard arable crops, and then we're talking about Europe. But we are also focusing on, for example, Africa, where you have all the crops depending on water. So it doesn't matter which crop. There is no crop if you cannot irrigate. And in that way, then drip lines are most favorable to start your irrigation. Also, wadi monitoring. A wadi is low places in municipalities, in urban areas. Well, we have those in Holland, and then like we're having this year now, high rainfall this spring. If in the urban areas there is a lot of rainfall, then there is a risk of flooding. That's why there are wadis, so those are shallow areas. But if those shallow areas are not completely empty when the next big rainfall is coming or expected, then the municipality could act on it and preventively already pump these or start pumping in these wadis to prevent flooding of the rest of the city, for example. Well, no wonder landscaping, gardening, yes, they can, of course, use these sensors very well, and of course also in golf courses. And landscaping, gardening, also we're aiming in a later stage for the normal consumer, and then don't have the long extended sensor, but maybe only with one cell, so that a gardener, somebody in his own garden, can see, okay, how is my grass doing? How are my plants doing? Just to get an indication, do I need to water or not? At the moment, we have about more than 500 of these sensors deployed, and that's the sensor only. That's not the sensor with the LoRaWAN. This year, we're starting with the LoRaWAN. These sensors are now already deployed in the Netherlands, England, Poland, etc., in various agricultural crops. Most important, and this is the part that we are really focusing on. What is important? What do we want to do? What do we want to show? And this is also in cooperation with our users. What do they need? Well, the first need is, of course, easy access and actionable data. So easy access, it's an app, it's always there. You can share it with your workers, etc., etc. And actionable data, no difficult graphs, no, it's red or it's green, for example. So red means attention and green is good, and then blue could be wet. So if you're looking at the examples that I have here, the large one, it's still green. I have 23 millimeters still in buffer in my 50 centimeter root zone. And the other one, it's in my 50 millimeter total buffer. The other one is almost full, 49 millimeters, and the 7 shows red. Here I need to irrigate ASAP, because with my standard evaporation of maybe 7 millimeters today, I'm still having a small buffer, but tomorrow it will be empty. Detailed insight, of course, all the data is there. So if you want to, you can have a more detailed view. If you're looking then at the lines of the water uptake, a moving line, moving like the yellow one in a rhythm going down, it means that there is active roots. It's uptaking the water, which is also for the gray line and a little less for the red line. If I would have a 50 centimeter one, maybe the 40 would be a straight line. And from that, I will conclude that at the 40 centimeter, at that moment, I don't have root activity. And this is another way to present the data. It's not only on the mobile app, you can do it on the computer as well. Then you have more possibilities to show data and to act with the data. Like I said, it's important. A farmer doesn't work with one platform. A farmer works with maybe 10 platforms. So he wants to share the data, use an API, give view rights to other users, etc., etc. We want to be transparent in this. There's no secrets behind our data. If you are a customer, you can share the data with whoever you want. And as I said in my talk about the soil and about the ways of irrigation, the drip irrigation is the most favorable one for optimum water use. Well, with a drip irrigation setup, there are many valves, sensors involved. And the new thing that we are doing in cooperation with Times, you see the blue box in the left bottom corner. The blue box represents the water that's coming out of the field. So if there is too much irrigation or too much rain, then you will have the deep percolation, the water leaving the root zone. We are going to catch this water, and that's not going to be just water, it's going to be nutrients as well, and measure this content of nutrients and reuse this in your drip irrigation system. So in that way, we'll make a climate smart application. So we will switch the pumps, switch valves, monitor and the pressure and flow within the drip irrigation system. So we can see how much water is going in, how much water is needed, of course, based on our soil moisture sensors. We will measure pH and EC to have the proper fertigation, so the proper amount of nutrients to give to the crop. And we will catch the deep percolation. The deep percolation in this case is the drain water. And this prevents environmental impact because the leaching of the nutrients outside of the root zone would otherwise cause environmental impact. We'll catch this water in big buffers, and we will, of course, monitor what's in this water on nutrients and reuse it for drainage and for irrigation. Well, and doing this in the Netherlands, we're testing this system. We're going to test it EU-wide next year. And for this, it's ideal to do that with LoRa. We will have the gateway on the site with the drip irrigation, with all these sensors, actuators, and then have a local controller. So without any outside interference, it can still operate. Even if we don't have a connection, it can still operate. As soon as the connection is back again, we can control, we can have management. I've done this in the past, not the drip irrigation, but I've done the sensoring in the past in many countries all over the world. There's always issues with 4G or with any kind of connection that you could lose a connection for a brief period of time, or sometimes for a longer period of time. If you then have a drip system like that I just presented, then you don't have any control and the whole system doesn't work. So that's why we are using a local LoRa network with a local controller, which we can remotely manage. And then we'll use the internet that's available on the farm. We'll use the mobile internet 4G. And if both are not stable enough, we can still use the satellite IoT like Lacuna is having. So that's why we are very happy to work with Onethinx, and that's how we want to give the best solution possible to farmers using this smart irrigation. Thank you. That's my presentation. I will stop sharing. Questions? I can already see many questions.
Thank you, Altio, for your amazing presentation. We do have some questions for you from the audience.
Yeah.
So, do you also have to control irrigation to grow the roots into the right layer?
Yeah, that's a very nice and tricky question. That's always also a discussion with a farmer. I was a farmer myself, and then there is the chicken and the egg story. Do I give water or do I let the roots search for the water first? That's difficult. That's difficult to decide. How much water is coming in the near future that I can depend on without giving irrigation? Yes and no. We cannot control the way the roots grow. The roots grow only there where they can find water and they can find nutrients. And roots will not grow anywhere if there is a compacted layer. So that's the whole, how to say, there's a balance in between. So you don't want to start your irrigation too late. And yes, at that time you might be pampering the crop, but if you don't, you're losing your optimum production.
Farmers around the world, they face different challenges. What was your biggest challenge as a farmer, your experience?
Water. Water is always the challenge. When do I irrigate? Do I wait on the weather forecast? Well, like I say, I was a farmer a few years ago, but from the time I stopped until now, the weather is changing a lot. The weather forecasts are more unpredictable. So what can I depend on with my irrigation? Do I get rain timely? And then even here in Europe. It's not that critical yet, but looking into to Egypt, looking into Africa, looking into Suriname, in Argentina, in China, India, then it's very difficult even to get any good weather forecast. It's very difficult to get water. You're in a dry place, so then water is always a challenge. And then you need, well, whatever you can get with the best decisions to apply whatever you can get.
We also made a poll for our participants, and from the biggest challenge for farmers, there were answers like monitoring the data
Yes.
coverage with LoRaWAN, and power management. And it seems that monitoring the data, it's still the biggest challenge for them.
Yes, and that's why if you looked at what I explained, we don't want the farmer to worry about monitoring the data. We will do the monitoring of the data. We just want the farmer to have a smart app in which they on which they can depend that we will give them a timely warning based on their own data. But that's also part of the training. That's a part of the understanding for the farmer as well, because it's a switch in his mindset. It could be that the farmer is used to give irrigation, for example, every 3 days with a certain amount. Well, maybe when he starts using the sensor, he can see that every 3 days a certain amount is too much, or maybe too little. So it's going to be a shift in management. You only want to give irrigation based on the data, based on what is needed.
How quickly do farmers like adapt to these new technologies? Is it like easy to use?
It's easy, it must be easy to use. It must be easy to use, otherwise farmers won't use it.
So you can say that it's you have good experiences with it.
Yes, yes.
And use cases.
Yeah, that's why it's on a mobile app. That's why it needs to be simple. It needs to be simple, and the farmer does not need to be worrying about his data, about his network, etc. That's all been taken care of. All he needs to do is check the app, and even the app can give him a timely warning, can give him a push message.
Okay, let's see if anyone from my team has any questions for Alcio. Now is your opportunity. Yes, so can you tell about some use cases around the world? Maybe can you elaborate more on that, like specific
use cases? Well, it's the same use cases like our users. It's used widely in potatoes. Many big potato processors, they stimulate their farmers to use sensors, because these potato processors, they want to be sure that their factories are operating on good potatoes. But it's also used, for example, in sugarcane in Sudan. In Sudan, they have sugarcane and they use flood irrigation, and using a sensor reduced their water inputs by 30%, which is a huge amount. But it's also used in greenhouse in South Africa on tomatoes. So it's used widely in many crops in many places.
Thank you very much for your presentation and for answering to our questions. Okay, maybe.
Okay, you're welcome.
So for participants, stay tuned, please, as we will be giving away our Smart Farming LoRaWAN multi-use kit, Sprouty. And also, if you stay till the end, you will be able to see our colleague Tom as well, who will be measuring the temperature of his own coffee, like the last time. So stay tuned. Alcio, would you like to add anything to your presentation?
No, that's it's all fine. You can find us at greenthinks.nl for more information, and there's an email address there. Just ask me anything.
Sounds amazing. I suggest we take 5 minutes break, just for the participants, and we'll be back soon. Thank you very much, Alcio, for your presentation. We really enjoyed.
Thank you as well.
From smart farming to LoRaWAN satellite, let's welcome Dario Buma, Product Manager from Lacuna Space. Hello, Dario. The word is yours.
My microphone unmute, everything set, good to go. Thanks, Anita. Also, thanks, Aljo, for the nice presentation. Really gives insight. Lacuna is all about satellite communication, data transfer, less about the real applications. So we're always very interested to hear about those. I will be giving today a general overview of Lacuna, introduction Lacuna Space. Some people know Lacuna already, so it's also good to give an update on what we have been doing. We haven't been out there always in the press, but a lot is happening in the background. I will do an explanation because, as some of you know, we do LoRaWAN, really real LoRaWAN over satellite. So the same stuff you do with terrestrial, we do over satellite. Some satellite basics for the people that are interested, not too much detail. Some use cases. Well, we've seen already a nice use case, of course, for agriculture from Aljo, but where would you deploy satellite LoRaWAN? And then a short intro on how to get on board with Lacuna technology if you want to play around with Lacuna technology. And in the end, of course, some time to do a Q&A. Introduction Lacuna. So people that haven't heard about Lacuna yet, we were the first company doing LoRaWAN from space. You see more people or companies using this technology these days, but we are the first. We think we're the A brand, and we think we can show we're the A brand. Our first satellite, that's also historically, was placed in orbit on April 1st, 2019. And this is was a low orbit satellite, and these satellites have a lifetime of about 3 to 5 years. So this first satellite is already burnt in the atmosphere. So that's interesting. There's not many companies that can say that. Satellite companies can, but IoT satellite companies, so we've been around. We have offices in UK and in the Netherlands, and have a global customer base. So we operate all over the globe. We have tests going on, for example, at Antarctica. There is no continent we haven't covered yet. I'm product manager within Lacuna, and I've been active since 2019, just some months after the initial launch. And I must say I really enjoy working there. So it's a pleasure to do business. What has been going on? So we are already in business for a long time, and the first satellite we did was already in 2019. This was funded by UK Space Agency and European Space Agency. And also our next launches are funded by the space agencies, also with private money. So we have, in the background, we're working on 6 more launches for 2025 and 26, end of 25. And these will be our next generation. We're already at generation 4 and 5. And every time, we do a new batch of satellites, we will, of course, make improvements. In the background, we've also been working hard on regulatory and certification. So we have, maybe Rock can show it. We have a nice device, an LS300 device, and this device is, I explain later on a little bit more about it, but these devices are certified. You can use them under FCC regulations, which means in Latin America it runs FCC. In Europe we use, of course, CE certification. In the UK we use UPSA. In Brazil, Anatel. So we've been working a lot on that, and also on the regulatory side, because doing LoRa with satellites also has challenges in that sense. We've been working also on improving our network, and that means that you have to not only say like the satellite is there, but we also have to monitor. So we're working on that. And we've recently launched S-band service, and that's an interesting one with a partner, Omnispace. So we also run our technology on the satellites of a third party. And this satellite, this is another type of satellite, but it shows that we are very versatile on that. S-band, not everybody knows it, but this is the 2 gigahertz band. So for the 2 gigahertz band, this is licensed spectrum. This LoRa operates in 915, 868 unlicensed spectrum. S-band is licensed spectrum. And the interesting thing is that we use the same LoRa hardware for this. So the LS300 device, it can communicate with standard terrestrial LoRa. It can go to the satellite. It can also do this S-band, and it's all based on this standard commercial off-the-shelf chips. Or circuitry. We've also been working on our tooling, so we have more elaborate dashboards and support you need if you want to deploy services to have reference if your performance of your devices are okay. We have developed software libraries, and we have tools for third-party vendors to enable our technology into their products. So this is what has been going on in the background. This is what it's all about. To the right, the picture, and this is in the non-clear case. Let's get this one. Maybe Rock can show. This is all that is needed to get to the satellite. Of course, there should be a battery in here, but it's if you see, it's 2 layers of PCB. The top layer is the antenna, and the bottom layer is also the antenna, the ground plane of the antenna. But it's standard LoRaWAN hardware on there, so it's a standard SX1262 chipset. Not in this case. For S-band we use LR1120, but these are standard commercial off-the-shelf so-called chipsets. This is standard stuff you get. So everything we do to the satellite is really sort of the same as what you would have with standard LoRaWAN, with a standard LoRaWAN device. Really, the only thing that is hardware-wise different, you could say, is the antenna. You need a special antenna, and it is not a very complex thing. So it's 2 PCBs, but this antenna is directional, and it has a circular polarization, and this gives us just a little boost we need to get to these satellites, because here on Earth you can do LoRaWAN for 50 kilometers, something like that. We need to cover, for the LEO satellite, I will explain a little bit later, 500 kilometers or so. And going to this MEO satellite, this S-band satellite, we have to do 10,000 kilometers. And we do that with the same power. Sort of in the same order of magnitude. We fit into the LoRa ecosystem, so any message you send via satellite, if you use TTN, it will show up in your TTN account. If you use another network server like ChirpStack, you could connect with that. We can deliver there. So everything from the consumer or the customer perspective is the same. There are differences. The satellite is not always there, especially these low orbit satellites. They pass around. I will explain later on, but the satellite with LoRa, standard LoRa, the gateway is always there. So if you send a message, the gateway will pick it up. If you send a message to satellite, you need to know when the satellite passes. Also, satellite LoRa is uplink only, so you can only uplink message. We do downlink, but the downlink information is for service related. So this with the downlink, is more like a broadcast where we give information on how many satellites are in the constellation, when a satellite will be where. And another thing that is a little bit different is that these satellite devices, if you deploy them, they need to see the sky, sort of. Okay, they can operate through canopy, even through heavy canopy. We've done tests with that, but you in generally need to put these devices outside, so it's not suitable for deployment inside. Satellite, and I made an and instead of versus, because satellite and terrestrial LoRaWAN really can coexist, and we see that in a lot of scenarios. So where you have also with LS300 device, where you have terrestrial LoRaWAN coverage, you can use that. And when you go beyond that coverage, you can go to the satellite. So these satellites, they have global coverage. And so anywhere where you put a device, you can reach the satellite with just normal standard LoRa devices. Of course, if the regulations, that's another story, but technically we can all over the globe, we can, wherever the device is, in Antarctica, in Australia, in New Zealand, just put your device and it will be received by satellite. Short introduction on the satellite basics. So what's happening with these satellites? On the left, the picture on the left, you see a constellation. Our constellation is not that large, but what you see is that satellites, LEO satellites, and that's because of the metrics, they orbit at around 550 kilometers, 500 kilometers. And that means that they pass the globe around 20 times a day. This is if you float at 500 kilometers, it will be 20 times a day. If you're at 10,000 kilometers, then you will pass twice a day. That's the difference. So LEO is low Earth orbit. That's the 500. Those are the satellites we operate ourselves, and these operate in SRD spectrum, the standard LoRa spectrum, and the MEO satellite, that's of our partner Omnispace, that operates in S-band, but that's at 10,000 kilometers. So there's a difference over there in the duration of the passes and things. The picture on the right, you see what's happening when the satellite passes. So what's happening, the satellite has a fixed orbit, you could say. It just circles around the Earth. And the Earth, in the meantime, is rotating. It rotates every 24 hours, day and night. It makes one turn. And while the Earth is rotating, the satellite sort of scans the globe. And what we see is that these paths that the satellites go over, they do not overlap. So you need to do a calculation on where is the satellite when. So this is a two-dimensional representation, and this is the story of Lacuna. And the story with satellite is, when can I transmit? When do I transmit? Where and how can I know when to transmit? I need to know two things. I need the time. I need the time. What time is it now? And I need my location. And ultimately, I also need the location of the satellite. So what we do is we broadcast information, and you need to receive that once a week. You broadcast information about where the satellite, how the constellation looks, and which satellite will be where. And we have a software library that takes care of that. And you input that information, you input your own location, and you input the time. And what the library will do for you is say, oh, if you're in this location and this is the time, then the next satellite pass for you will be in 20 hours, will be in 20 minutes, will be. So what happens next is that your device goes immediately back to sleep. As soon as it knows, it goes back to sleep, and it wakes up, either get the sensor data, so measure the humidity in the soil, or the nutrients that are in there, or whatever parameters you want to measure, go back to sleep, and wake up when there's a satellite to send the data, and then go back to sleep. That's what we do. And that's why we work with this Almanac. Other satellite systems, they work with the Beeman or traditional satellite system. So what you would need to do as a device, you would need to listen to, if you hear the satellite, and if you hear the satellite, you know it's there, and then you transmit. But that's very power hungry, and that would eat a lot of battery capacity. And what we are doing is really make it low power, and that you can in theory have multiple years of battery life. So the footprint is about 550 kilometers. What can I say more about these low Earth orbit passes? They are about 60 seconds to 2 minutes in duration. So you have to be fairly accurate with your timing, or you just miss it. And these higher elevation, these medium orbit satellites, they have longer passes. They last for hours. So between 1 hour and 2 hours, I would say. Back to, those were the satellite basics. Back to the use cases. Well, typical use cases, where would you deploy satellite? Of course, you can use it in an urban area. If you have a clear view of the sky, it will work there as well. But we target specific remote locations. And there's several figures out there, but it's about 70 to 90% of the globe has no network coverage. And of course, we now get with SpaceX, we get this satellite, but this is really another order of magnitude. These are broadband connections, and these are very power hungry. What we target are remote locations where the major cost of your device is probably the deployment. You deploy it once, and then it should stay there, and it stays there until the batteries deplete, or until there's too much dust on your solar panel. And so these are really remote and really need to be low power. Other use case that we see is, again, remote locations, but deployments where you have a distribution over a large area. Think of a river where you every 10 kilometers want to do a measurement. Then you would have a very distributed area, and it is very costly to do either a 5G, 4G infrastructure, or with LoRaWAN gateways infrastructure, because you would need more power to do that. And other use case we see is that people, and I will explain a little bit later on that, the relay solution we have is extend the reach of terrestrial networks. Sometimes you can, for example, you have good reach within the city, and at the borders of the city there you just cannot reach these 5 last water meters, and to put a whole gateway over there, that's very costly for these 5 meters. But then you could use for example this LS300 modem in a relay mode. This one we already covered with, in this case, it was Entutech, the picture over here, but this is typically plantations, forestry, soil monitoring. We see also carbon sequestering customers doing, having to measure stuff, and this is ideally, or the ideal solution we have for this remote. Tank level monitoring. This is what we do with a partner, IoT Ventures. They operate in, they come from New Zealand, Australia, and they operate in the Pacific area, and they do water monitoring. This is a vital resource, of course. If they run out of water, they have to, if there's not enough rain, they have to supply it by boat, and you need to monitor the levels of the water. So this is critical infrastructure. Also use case, this is what the LoRa is also used for. But if you have remote deployments, when do I need to empty my bucket, or when do I refill the tank? Instead of doing your fixed round, you go at when you see the bucket is full, or your tank is empty when you refill. So this is also a use case. And I still think it's amazing that you can lose this big of a machine, but this is also what we see is interest from mining, for example, but there's many more use cases, but these really speak to us. Of course, big machines, that you can track your lost assets. How can you lose a device like this? But apparently it happens. So they use it, they leave it, and then where was it again? It's easy. So real-time tracking is, of course, difficult with a satellite that's not always there. It's less suitable for fleet management, because then you need continuous connectivity. But for this kind of tracking, it is also ideal because it's low cost, low complexity, and it runs on batteries for years. So next one, how to, if you want to do something with Lacuna technology, we have several ways of integrating or getting to the network. Just like with a mobile network, you need a mobile phone, and to get to the satellite, you need a device. So I've shown the sensor, the LS300 sensor box device. We have a relay, smart antenna. You can develop your own soft and hardware, or you can buy, of course, a Lacuna-enabled product from your favorite vendor. And I know a favorite vendor of us. They host our seminar here. I will give a little bit of detail on each and what they are used for. So LS300 sensor is really our product to get acquainted with Lacuna technology, and it works with it. It's just configuration. You don't have to code anything. Devices are pre-certified, so you can pretty much use them globally. It's self-contained. It runs on standard alkaline batteries. It will not have years of life, but it is, especially with this type of battery, but it will be good enough to do proof of concept, show what it can do, if the sensor works in your condition, if you can use in your situation the satellite. Maybe we have people that want to mount a satellite antenna on the back of a bird tracker. You can try. We always recommend use this antenna, but in some use cases you say like, okay, it's not important that we receive every message, or we have a much lower service, so any message we receive, that's also okay. So you can play a lot with this configuration, and LS300 sensor product we have is very suitable for that. So it's configurable, and it allows you to play around with how does this satellite network works, how many satellite passes do I get, that sort of thing. Can I go through canopy? Also, I get to that later on. We have the free software library available. So also on the standard product, if you say I remove the software, you can still run your own software and make your own applications and run them on this platform. But you can also do that on basically any other LoRa enabled platform. Relay is something new. So what we achieve, it's really pretty much the same as the LS300 sensor, but it's focused on a different target audience. So major change, or the big change there, is the software. So Relay runs this so-called Relay standard software. And what is interesting about this software is that you can use existing LoRaWAN devices with existing pigtail antennas or embedded antennas, and these devices, if they adhere to this new relay standard, and this is an official standard from the LoRa Alliance, and for most devices you don't need hardware changes, so you would just have to do a software update. And what the relay does really is, because relay is battery powered, it's asleep most of the time. What you do with this relay standard is wake up the device. Just before you send the data, you send a preamble, and the device listens at regular intervals to wake up. So it's a mechanism. You could say it's a gateway, but it's not. Its use is limited. So a gateway can service thousands of devices, hundreds of devices, where a relay can relay data of tens of devices, and maybe you can up that a little bit if you have data that only has to go once a week or once a month. Then you can do more devices on one relay. But the relay is really, I would say, I would call it a poor man's gateway. But the great thing about it is you can deploy. It's battery powered and it's self-contained, so you can put it somewhere. It receives data from one LoRaWAN device, other LoRaWAN device. It puts it in its queue, and when the satellite passes, it will pass on this data to the network. And here we follow the official standards, and what you see is that there's already parties making relay capable sensors. We see that the LNS providers like ChirpStack, Things industry also support this this standard, so it's really transparent the way we do it. So you wouldn't your end device would just send, and in the back end you would just receive the data as you would normally do. There's the magic is happening in between in the network. Smart antenna, that's also something on the list. It's really LS300 with a cable attached to it. We provide a separate kit for that. We have a lot of demand for this, that people say, like, I just want to use LS300 as a low-cost backhaul. You have other means of backhaul. For example, you can do 4G, but sometimes you don't have 4G. Then it's in some cases interesting to do that via serial cable. These products will be, or these kits will be available in Q3 of 2024. LS300 sensor is available today, by the way, and relay we are doing a technology preview. I think in the next month that will be available. The next way on getting on board is we have to support third-party hardware vendors. Think about what if you use. I should show products from the competitors, of course. Seeds, anything that has a LoRa SX1262 or LR1120. LR11-2X chip on it, and that's of course Greenthings and Onethinx can run this software because it's just LoRa. We provide a software library for that, and this software library enables any third party to incorporate this Lacuna technology. This library takes care of any satellite specific stuff. So this library, you would have to port it to your hardware, and this is something I will show in the next sheet. Maybe we'll get there with Onethinx and Greenthings. But once you've ported it to your specific software stack, you can just say to the library, send message, and the device or the library will tell you when the satellite passes. It will do this automatic almanac update. So that's good. To keep things low level, we have Arduino version available for it. So you can just use also this LS300 device. You can just use Arduino and program in Arduino. So that makes life easy to get on board, at least. But there's also a portable version, for example, if we want to port to Infineon or other platforms. Minimum requirements we have for the platform is, of course, the radio should be SX1262 or LR11-2021 compatible. We need a minimum of 256 kilobytes of flash. Well, you can read it off the screen just like me, but we really recommend to go a bit bigger. The minimal is what is required for the satellite stack, and if you have very minimal implementation, like I only need to read out the I2C sensor, and it sends a message every time it passes. If you need more business logic, you need also memory for that, and that's why we recommend going for something bigger. But it will run on anything that Onethinx can offer over there. And this is, of course, the preferred way for Onethinx and Greenthings, is that you would just get a solution from Onethinx that would be Lacuna enabled, and really that is the software stack, the antenna, and then you get to satellite. But I think you get the message. That's it, sort of, for me, and I'm happy to take on questions or detail. For more info, you can check out our website. I heard that it was down just after the previous seminar, but it's back up again. And if you want to reach out to us, you can use the above email address, and make sure you mention the Onethinx webinar in the subject. Then we know what it's about. So that's sort of it for me. I go back to the main screen. And
for your amazing presentation, Dario.
Thanks.
Now we would also have some questions from our audience. So shall we just start with Sujit Anandan? So the location information to match the satellite path has to put in the sensor during deployment. How to change it later?
Sorry again. I missed
So
the
the
beginning.
location information to match the satellite path has to put in the sensor during deployment. How to change it later?
If you have a static device, then you can just put, when you configure the device in the field, you can just say the device is here and the location doesn't change. So that's easy. If you have a device that moves, then you would need some sort of GNSS. So the LS300 device I show, we have a GNSS in there that makes it easier that you don't have to configure that manually. But in principle, you don't need GNSS if your device is in a fixed location. You just tell it where it is.
So another question, how the communication actually works. There is Lacuna gateway in between the satellite and Onethinx module.
If I talk, and I call it standard or terrestrial LoRaWAN, if you go with terrestrial LoRaWAN, you go from your Onethinx device, you go to the gateway, and the gateway is connected to the internet and delivers the data to your LNS, your LoRa network stack. With the satellite, we have sort of similar, but there's more components. So you go from the device to the gateway, but the gateway is not connected to the internet. The gateway is floating around and it receives the message, but it doesn't immediately send it through. It has to pass a ground station, but that's not true for S-band. We have the instant, we beam it down and it's instantly decoded, but it works really the same. So you send a message, and the only difference you see between a standard LoRaWAN gateway is the delay. For S-band, there's no delay or minimum delay. You won't even see the difference. The difference only there is the gateway is not always on or not always there. For SRD satellites, so the low orbit satellites, you have a delay. You receive the message and the satellite has to pass the ground station before it can link it down. But as soon as it's linked down, we forward it on to the network server, and we do routing, so we can route also to specific customers. For the LS300 standard kits, we route via Things network. You can get a free account and can test with that.
This gets us to another question, which is, what is the latency to reach TTN via satellite?
If it is, if we talk about S-band, the licensed, so the licensed spectrum, that's so-called, it's reflected, like it's like a mirror that the message goes up and goes down straight. So there's a couple of milliseconds, and with SRD, the standard LoRaWAN devices, you would get, it can take up to 24 hours, worst case, but usually it will be 12 hours maximum. And it depends on your location with respect to where's the ground station on the globe. So in Australia, it might take longer than in Europe. So it's difficult to say that. With our next generation of satellites, we will be having more ground stations. So that will instantly lower the latency. But the latency will be there, and it will always be hours, I foresee.
Another question from Ruth. Can you explain or tell me anything about the problem of the Doppler effect in this use case scenario?
I'm not, sorry, I'm a digital guy, so Doppler doesn't exist in my world. I know, and that's the stories I cannot explain, that LoRa is very resistant to Doppler, and that is it's ideally suited for these fast moving satellites. And I know that, yeah, it's not an issue for us. Maybe I didn't explain, but we use another modulation which comes from the same chipsets. We use for satellite. We use LRFHSS, and it's not because the Doppler effect, but it's because the satellite, it sees the half of Europe when it comes over, so it sees a lot, and standard LoRa might be limited in capacity over there. LRFHSS gives better tools for that. So Doppler effect, feel free to email this question, and then I will certainly find somebody within Lacuna to answer that.
Another question from Rock. Do you also have experiences with seagoing vessels?
We have one partner, and if it's really a vessel, that does sort of the LS300, but then on a buoy. They're called GRIN, and they have a Lacuna capable device that is mounted on buoys, on sea buoys. So it's a possibility, because the sea is very LoRa friendly, I could say, because there's not so much radio noise and background over there, so it's nice and quiet there.
This is amazing. Then we set some just administration question. If we can get access to the software without needing to buy Lacuna hardware, or what is the price of LS300 cost? Yeah, 300.
So the pricing, that is, I think it's 399 Great Britain pounds for the standard kit and the standard device. But yeah, that's the way we price it, and there's some support included in that. The relay will be priced slightly different, but I don't know if pricing for that. And the question on getting access to the software. So the software is not under, it's open. So it's not like you need to sign an NDA or anything, but we limit currently the deployment because we get lots of support questions and we cannot handle those. So the only way to get access to the software at this moment, unfortunately, for the people that want to get access to it, is via somebody that has a LS300, or buy a LS300 and you get access to the dashboard and the forum and the tools. Because if you have the software, you also need to register a device to get to the satellite, and you also need tools for testing, and all that sort of stuff is included with the LS300 sensor kit or the relay, and that's really, otherwise we can't support it. So there's the software part, and there's the service part, and the service it doesn't work. Why doesn't it work? It could be anything, and that's why we also say, like, if you want to really get started, get something that counts as a reference. And it could very well be that if we reach agreement with Onethinx, that you say, like, buy a device from Onethinx, that can also serve as a reference. But we need to be very certain that if we get approached for support, that it's somewhere in the network. And that's the nice thing about the LoRa ecosystem. It's not vertical as classical satellite, like you buy everything with us. No, you can buy the device here, you can buy the software there, you can buy that over there. But it also means that we need a good layering, and this is the way we can do that at the moment.
Thank you very much, Dario. One final question before we move to another speaker. If there are too many devices in the same location, for example, Europe, sending at the same time, how do you handle that? Is there any loss in data?
The loss in data is just like LoRaWAN. LoRaWAN doesn't give you guarantees that you in all circumstances get the messages in. So we have no concerns for capacity, that we ever reach capacity. I have on my rooftop lots of devices to test with, but there's the only thing we do is keep them separate by 60 centimeters. Otherwise, you get Fresnel interference. That's stuff. I shouldn't use these terms because I don't know what they mean, but they say keep them separate. But that's not an issue. We don't see that, but it is just like standard LoRaWAN. We use LRFHSS, which is higher capacity to start with, and we aim for why would you use satellite if you can have a local network? That's always the question.
Thank you very much
for
your presentation and your answers.
Yes, thank you for giving us this opportunity, Anita.
Thank you, and I hope to see you soon in the future in some other event.
Bye-bye.
Bye-bye. Before we move to another speaker, stay tuned as we will be giving away our smart farming LoRaWAN multi-use kit, Sprouty. And if you stay till the end, you will be also able to see Sprouty in action, actually how it measures the temperature of our thumbs, of our colleague thumb coffee, like the last time. So this is just the funny part. Keep asking questions, and for the most innovative questions, we will also be giving away Sprouties. So before I welcome the speaker, I would also like to introduce my colleague Tom, who will also talk more about the Onethinx module, which uses Infineon PSoC 6. Please.
Thank you, Anita. Hello, everyone. Later we'll talk and we'll have a workshop on the Sprouty that you see here. If you haven't already, I would suggest you to go to our GitHub page where you can follow the workshop introduction to get started with your Sprouty, so you're ready for the workshop. And before, as Anita said, we give word to the next speaker, I would like to mention that our module, Onethinx module, uses PSoC 6 because it's very flexible and very secure. So stay tuned for the workshop, for the next presentation, and as Anita said, you will see me measure my coffee's temperature since I don't have a soil at hand right now. That's it from me. Thank you, Anita.
From satellite LoRaWAN to Infineon PSoC. Let's welcome Srikant Nereva, Senior Product Manager from Infineon. Hello, Srikant.
Hi Anita, hi everyone. Thank you for being here, and thank you for the opportunity to talk about PSoC 6 here. And yeah, hi, myself Srikant Nerella. I am a product manager at Infineon Technologies. I handle Bluetooth MCUs, and I am happy to work with Onethinx to integrate PSoC 6 into the Onethinx module and enable such cool use cases that we have been discussing so far. And with that, let me get started. Okay, so yeah, I think this is up. Okay. So Infineon, if you're not familiar, is a global company driving decarbonization and digitalization together. And we have ambitious targets by 2030. We wanted to achieve carbon neutrality and also greater savings in terms of the by achieving digitalization together. We keep that into action, and some of our products or most of our products are already tuned to realize this goal. And within Infineon, we are from ICW, which is under CSS division. And a little bit of history. Infineon has acquired Cypress Semiconductors, which has also acquired IoT division of Broadcom. So that's the history. And as part of this strong community that we have acquired over the companies, we have built a solid expertise that is required for IoT product development. And when it comes to wireless industry, a lot of applications or a lot of protocols are driven by standard bodies. Okay, so you can name it like Bluetooth Special Interest Group, Wi-Fi Alliance, Matter, or CSA, and a lot of other forums. And Infineon is strongly present in all of these bodies, and we drive the product development or protocol development by working with industry leaders. And also we have like a strong portfolio that comes with decades of expertise, well matured within the industry, and enabling our new roadmap products. And as a company and as an ICW division, we continue to invest heavily into our products, capacity, people, and IP development. We made a couple of press releases. We have invested into additional capacity in infrastructure by looking at based on the uh, pandemic situation. We see a need to ensure stable supply of silicons that are required for the market. Otherwise, it is going to create a chaotic situation. So this ensures at multiple nodes that we design across all the nodes, all the technological nodes, we have a stable supply of silicons. And in terms of people, we have a strong solid base of R&D and marketing spread across the globe, and we have doubled the team sizes with an IoT product line, and we continue to develop products into advanced technology. So most of our products today are using 40 nanometer, and upcoming products are getting on to 22 nanometer technology node. With that, I will quickly get into the product view. This is a quick snapshot of Bluetooth MCUs that we offer. And on vertical scale, it is a increasing MCU capability, whether it is CPU bandwidth or in terms of peripherals and number of IOs or memories that are available in the final MCU. And on the horizontal axis, you would see Bluetooth capabilities. In Bluetooth world, it is not just sufficient to compatible or sufficient to get certified with the latest version. It is also required to support all the features that are available in the spec. So for example, any device can support like latest and greatest 5.x version, but may not have all the capabilities implemented in the hardware. So that's why it is critical to look at whether that particular product is also supporting the required hardware feature. For example, 2 meg PHY or long range support, or something like a PAWR, which is very recently launched, something called periodic advertisement with response. Okay, some of these new capabilities that are added by Bluetooth SIG are enabling cool and innovative applications that we see in the market. And so coming to the products, in the starting range, we have PSoC 4 Bluetooth LE, which brings in our strong MCU expertise that we have, which is a programmable system on chip. So it's nothing but a MCU paired with a mini FPGA sitting together with the MCU. So you can program a PDL logic and create a customized end system architecture. And this also helps in avoiding surprises or last minute PCB respins. Thereby you can save cost and time to market. So that's where all our PSoC portfolio brings in. And PSoC 4 BLE comes with a 1M5 support. Is primarily Bluetooth generation 4 device. And on the next we have CWW 20835 and CWW 20820. Both of them have ARM Cortex M4, which can go up to 96 megahertz, and also they support 2 meg PHY, enabling higher data rates, and internal power amplifier, which can transmit at a very high transmit power. Thereby you can establish or maintain connections at far distance. And the primary difference between these two is internal flash. 20820 comes with an integrated internal flash, whereas 20835 has a large ROM which hosts our software protocol stack, and thereby reducing the flash requirement on that. And the next one we have on the line is PSoC 6 BLE, which is our focus today. And this is our major horse and pretty famous product within our product line. It is a dual core, comes with a CM4 and CM0 plus, and supports 2 meg 5. And also it has got a lot of compute power. It can go up to 150 meg speed, which we'll talk about it later. And last not but least, so our new generation product, okay, this which is just launched very recently this year, is a CYW 20829. It offers dual M33 cores, and it supports all the features that are adopted until now in Bluetooth Low Energy. So until 5.4, every feature that is part of the spec is available in this product, and it is pretty cost optimized, and then pretty low power optimized, that enables applications. And the major difference is PSoC 6 is for high compute needs, where you need to drive displays, or you need to run a lot of algorithms. PSoC 6 BLE fits very well in that. And let's look at a next level details into PSoC 6 Bluetooth MCU. So what it offers is low power design, purpose built for the needs. Whenever we talk about IoT nodes, we have two extremes, or a mid extreme, right? So there is something that is with application processes which runs Linux, and then it comes with a bulky power budget requirements, thereby may not be able to enable battery powered applications. And at the same time, we do have like a very low end MCUs, which are like a CM0 or bare metal MCUs, that are used for simple applications like a beacons or tags that may not require a lot of compute. Okay, but as we see, the industry is evolving with more and more needs for the security and compute to bring it to the node. So what do we mean by that? If you have a IoT node which is gathering a lot of data, a lot of sensor data, and you have to pass it on to the cloud to run certain machine learning or any algorithms, and then take any actions, it is going to compromise on two things. Okay, one is data privacy. You're passing all the data to the cloud, and also it increases your cloud services cost, because your demand on the data transfer is high. So the new trend is edge IoT, where we are bringing that IoT processing towards the edge, and we would like to run machine learning in the end node itself, and process all the data, and only summary actions or results are sent over to the cloud. So thereby you can save the cloud cost, and you can address security and privacy risks that are associated with IoT devices. And that's where the PSoC 6 BLE fits very well, where it brings in the optimal compute to 150 megahertz, where it can run machine learning or even any other complex algorithms that are required. And also it has got a lot of flexibility for low power, where you can scale down, and you can run it at a lower speed, and reduce overall power consumption when you don't need processing, and you are just using it for a data collection or for a simple Bluetooth networking. And also it comes with a very platform level security, which we'll talk soon. Okay, so let's take a more closer look at this product. As I mentioned, it is a high performance and low power. So the dual core architecture with 150 meg also comes with a choices of ultra low power and low power modes, wherein you can scale down the core supply voltage using an API, and thereby overall system consumption comes down, and you can run at a very optimal speed that is required during those states of the application. Or whenever you need higher processing, you can scale up the bump up the voltage, and then increase the frequency, and run it fast, and go back to sleep. So that way you have got a flexibility to choose between both high performance and low power as per the application needs. And Bluetooth connectivity, it is 5.2 core compliant and supports 2 meg data throughput sub rate. And security is a fundamental architectural level. It is integrated where it has got a advanced crypto engine which supports AES and SHA, other accelerators, including a random number generator. And then there is a built-in eFuse where you can store secure keys that you would like to establish root of trust. So this is something like as a end developer or end product developer, customer can program the unique key in the production environment into the eFuse directly, and those keys are established via private channel, and that's where you can ensure root of trust is maintained to the production life cycle. And a lot of tools that can enable over the air firmware update with a secure protocol. In addition to all these fundamental pillars, this product also comes with a strong integration. First one to talk about, there was a CapSense, which is industry proven to application to enable HMI applications, where you can implement a touch interfaces, touch buttons, or proximity gestures using the same MCU. You don't need a additional extra MCU to implement those such HMI functionality. And it can drive segment LCD displays, and has got a something called a smart iOS. It is again a proprietary or glue logic that is available with the iOS, wherein if you look at a generic iOS, you can just simply toggle them like a high or low. But by using the smart IO, you can implement a logic where you can implement AND gate, OR gate. You can mix a couple of IOs together and create a custom engine that is running with those IOs. Thereby, you can actually save BOM cost. You can save some passives that are going into the PCB, and also it offers more flexibility and more creative ways of designing end product, right? And the next one is UDBs, Universal Digital Blocks, which are the key part of that programmable system on chip, which you can configure and you can implement FPGA logic. And then digital blocks and digital peripherals are whatever that you see across the MCUs in the industry, but it has got a more which you can configure. For example, there is something called a SCB, serial communication block. A same block can be used either as a UART, SPI, I2C buses. Okay, so now you have a choice. Okay, how many UARTs or how many SPI or I2C interfaces that you need, and you can customize overall all the available SCBs as per the need. And also it has got a USB subsystem, it has got an audio subsystem with the I2S and TDM and other capabilities. And it comes with a variety of packages like WLCSP, BGA, QFN packages, and some of these packages are enabling very small scale designs. Even things like smart rings, which are like a very small in size smart rings, they use PSoC 6 BLE. And also we are into fitness bands and other applications that require small size form factor. A summary of what I have explained, which is performance and power flexibility and robust security for your products with isolation of the hardware resources. You could establish a secure embedded system design, and also comes with a lot of integrated on-chip peripherals that will reduce your system cost. And again, CapSense, which enables sleek touch-based HMI interface, user interface designs. And it is pretty versatile. I mean, this same product is going into many varieties of applications, whether it is industrial, consumer, or some of the automotive related applications as well. A snapshot of the power budget or power consumption, how it looks like, so that you get a fair idea of what we are talking about. When this particular CPU is running at a peak frequency, 150 meg, processing all the complex algorithms, it takes up to about 5.8 milliamps. And if you're not really running any algorithms, you're just waiting for some peripheral interrupt, something like a sensor is trying to interrupt MCU. I mean, during those low power states, you take about 300 microamps, or even deep sleep mode, which is 7 microamp. With in deep sleep, you can still and be available for a quicker data transfers, or quicker reactions to the over the air events that are happening. And in that state, it can take up to 7 microamps. And if you don't need Bluetooth connection, you can just go to the hibernate mode, which is even further lowest power mode, and where you can wake the system either using a timer or using a external GPIO, like a user interaction. And during this state, it just operates with a very low leakage of 300 nanoamp. And once you wake up again, you boot from the beginning, and then you reestablish the connection and then get started. And also the wake up is pretty fast. You can see that within 500 microsecond, it wakes up from hibernate to active mode, and ready to process even complex state machines. Okay. Uh, with all of these hardware integration, or the cryptography integration, we also add additional security assets that enable platform level security infrastructure. So for example, we work with even some of the government bodies, and we get certifications like a NIST and others for this product, so that what are the new regulations that are coming into the IoT industry, that you can address with this particular product. Even things like it is a PSA level 1, and we are applying for level 2. So PSA is a platform security architecture, that is a standard model that industry is going towards to address the complex mechanisms of security. So what level of security that you need, you can understand by using a PSA infrastructure. So PSoC 6 BLE comes with the off-the-shelf security. To name some of it, it comes with a Mbed TLS security library, which provides ready-made algorithms and protocols that implement some of the certificate handling, so that you can go to design very quickly. We know security is a complex topic, and it doesn't need to have you go spend man hours of bandwidth or efforts to get into the production. So that's why we bring in ready-made libraries in our software tool chain. So next one is like a trusted firmware stack, that is also a industry proven security stack, and it is very well acknowledged in the industry, which enables applications that likes to get secure certifications. And all of this is also enabled with our driver library, which is talking to the hardware blocks, and that implements drivers where they can provide acceleration into the crypto algorithms. For example, if you talk about Mbed TLS or trusted firmware, whenever they use a encryption or other operations, by using these accelerators, it will improve the speed of execution, and also it will reduce your flash and RAM memory consumption. And apart from this PDL library, we offer bootloader, secure bootloader, and also a tool chain and middleware for device firmware mechanisms. So the some of these tools, I mean, all of these secure VOTA tools are also open source. So which means you can actually create a custom variant required for your own product on how to deploy a secure VOTA into the end embedded system application. So quick glance of what applications that we are enabling. So as I mentioned, like it is into home automation, HMI applications, wearables, battery powered applications, and portable medical. Again, the rich analog front end that is available, like ADCs and DACs, op amps, they enable a lot of medical applications that requires analog design. Okay. So I will spend a small amount of time on software and tools before I conclude on how we are enabling all of these rich silicon or hardware, the MCU that we have, how we enable that to end application, right? So something that we offer is Modus Toolbox. It is it is not really like IDE. It is a toolbox where you can take it to any IDE. For example, if you like to use Visual Studio Code, or you are fan of Eclipse, or you are fan of some other IDE, you can just take the configuration and use your own IDE and get started with the development. And whenever we talk about software, there are two sets of software when we work with embedded systems. One is the software, runtime software, that goes into the microcontroller, whether it is your libraries, drivers, or business logic that gets into the MCU. And we offer wide variety of libraries in our Modus Toolbox. Okay, whether it is graphics middleware, machine learning middleware, or USB middleware, and even Bluetooth protocol software, all of that is available, which can get programmed into the MCU. And when it comes to other set of software, which is a development tools, so these are the tools that are required for you to complete your application development, which is like configurators. For example, if you want to configure certain IOs as per the schematic, like you have created a new design and you wanted to remap GPIOs or some of the peripherals, you can do that. And there are tools like capsense tuner, where you need to tune the capsense performance as per the final PCB layout. So you can use this tool to tune the capsense performance and then get started quickly. And then other tools like sniffers, whenever you are working with the wireless protocols, there is a need to use a sniffer so that you understand what is going over the air and debug accordingly, so that where it is failing and what changes that you need to do. And the wireless sniffers are not cheap, so they are super costly, right? So we offer something called a Bluetooth Spy, a sniffer tool, which will help you to understand what is happening over the bus, and so that you can your debug is simplified. And again, that's just a snapshot of it. I mean, there are a lot of other development tools that are integrated into the Modus Toolbox. Okay. This is the a block level architecture, which is a repeat of what I mentioned. So when it comes to tools, these are all the tools. And then applications, we offer code examples, we offer reference designs. For example, let's say if you are implementing a remote control, a voice-based remote control, or you are implementing a keyboard, we have a ready-made design that is available, which you can just copy paste and then go to the production very quickly. And then all the middleware that I have discussed, including machine learning, graphics, audio middleware, and security middleware, and others. And fundamental architecture of like a board support packages, which are talking to the actual hardware and providing you the configurations. And we have a strong community within Infineon, that is Modus Toolbox community. Anyone can just join and you can follow through the community. We have across the globe support teams, and our customers and partners also keep discussing about capabilities and how to address a problem and how to create a solution in this community. So it is a wonderful source of information, and you would learn a lot, and even our customers contribute to this community, which helps us. And apart from that, we have like a very well documented guides and API guides that are available to get started quickly. I think I have covered it. I will skip this. So any tool chain that you can use, whether it is command line or graphic user interface tools. This is just a clarification of whatever I have mentioned. I think there are multiple terminologies that I have used. I just wanted to give a view. Whenever we are talking about a Cortex MCU hardware, there is a layer-wise development. For example, you can use something like a register level read and write if you need a very fine-tuned configuration, or you can use a low-level drivers that are like your read and write level drivers for each interface. Or on top of that, we have something called HL, hardware abstraction layer, which is enabling abstraction if you are moving from, let's say, a free RTOS into a different RTOS, or you are using a bare metal without any RTOS, and you are planning to move to RTOS. Okay, so some of that is simplified if you use our hardware abstraction layer APIs. And yeah, obviously when you use such abstraction layers, you may not have a flexibility. You need to go a little deeper down, and you may need to use next level of layers whenever you are implementing a customized solution. Okay, with that, I think I conclude what I wanted to talk about. PSoC 6 enabling wireless connectivity, security, and also working with other protocols that we have seen with Onethinx module, and enabling cool applications like smart farming. And now I'm happy to take questions.
Very much, Srikant, for this amazing presentation. We also welcome the participants to the Infineon community. The link is also in the chat.
Thank you.
Here now the questions from our audience. How does PSoC solve flashware, many flash rewrites for data that needs to survive power cycle reset?
Okay, so flash. Okay, so we have flash memory that is integrated into our product, which is very well tested. I don't have the number. What is the flash variant that we support? I think it is very large number. Okay, and yeah, I can take that question back and then understand what is the exact answer, but it should be in our data sheet. But yes, so there are two mechanisms. If you are reading and writing to the same location, yeah, you need to be within that number of read write limits that are available in the hardware, but that is also not a small number. But at the same time, we have some middleware called KV store and other middleware which does the ware leveling algorithms. Okay, so that maps out your flash usage, and it can dynamically swap across the flash locations and thereby reduce ware leveling and improve your product life cycle. Yeah.
Thank you. Another question. Can you name some applications where PSA certification is needed for an end product?
Oh yeah, so we have come across a application where PSoC 6 is currently used in something called what I call like a stethoscope. It's a wireless stethoscope, very cool application where you know doctors don't need to wear this stethoscope on ears. It is all wirelessly connected. You just put it on your heart, and then all the heart data is passed via cloud or via Bluetooth, right? And some of these medical applications, they need to go through government certifications, right? FIP certifications and other certifications. So okay, that's where we see PSA level 1 is important. and also applications like door locks, okay, where obviously security is important, right? So that's where it is needed. Yeah, not every application requires it, okay. It is always as per the need and driven by the demand of your market. And again, even in our customer base, we don't see, you know, more than 5 to 10% going towards a PSA route, okay. They do use security, but they really don't go to PSA level unless it is required, okay. Security is fundamentally used, and you can again include it whether you need it or not. But uh, it is all I mean, in security, there is a saying, right? Like, you know, it's like how much you want to defend, you need to invest that much of fencing, okay. So PSA also comes into that category, okay. So you can use it on need basis. Yeah.
I think it's amazing what you're doing.
Yeah.
Can you hear me?
Yeah, I can.
And so another question is, how is CapSense tuned for the material where your product is mounted in?
Yeah, I think that's a very good question. So CapSense being a analog block, it is pretty sensitive to the noise data, and particularly we have a product here which is using wireless as well as CapSense, right? So when you have a radio that is transmitting, you know, with such a frequency, it obviously impacts CapSense, okay. But we do have within the silicon, we have a good isolation and infrastructure, so that, you know, they coexist very well, okay. And when you make a final PCB, you can put the data into something called our CapSense tuner. It's an utility, and once you put your mapping and how you are using, what GPIOs you are using for the CapSense block, you can run the tuner, and that will log the data. It will take the data from your PCB, your end product, and provides you with recommendations what type of tuning configuration that you can use. Yeah, we have very informational videos and help guide CapSense. Yeah.
Thank you very much for the presentation.
Yeah.
I think we will move now to our hands-on workshop. But first, let me introduce again our colleague Tom, who will also thank you. Hello, Tom.
Hi.
Who will also elaborate more on PSoC and Sprouty. Tom, the word is yours.
Thank you, Anita. For those of you that have been watching from the beginning, you have already heard everything, a lot about what I'm going to say today. Firstly, I would like to say, if you haven't already went through the introduction, and I'm saying that again, I'm hopefully not too tiring, that you should go on GitHub and go to the Sprouty workshop introduction, where it shows you how to set everything up from PSoC Creator to VS Code, and it also has the Sprouty starting example. So it doesn't have everything, but we will go through everything in this workshop. I would like also to give a word to our CTO, Rolf, and maybe Rolf can explain a bit what is Onethinx, how Onethinx started, and what our goals are, and similar.
Yeah, thank you, Tomislav, for the introduction. Rolf Notenboom, I'm one of the starters of Onethinx, and that's back in 2016, so that's already a while ago. And I had an idea to make a module. So, or not that it started with that. It started a bit earlier that we were introduced to LoRaWAN, and we were at the Things conference. Yeah, LoRa was quite new technology at that time, so that was interesting for us. And I liked the way you could send data over a long range with very little energy. So yeah, you can send like 10 kilometers with a AA battery for over a year, and that's amazing. So I was thinking, okay, we can do something with that technology, and we can mix it with some nice stuff with PSoC, and then yeah, we can make a module of that. And so that's where the idea started. And so I started working on the development of the module, and I hooked up a PSoC 6, and I hooked up a LoRa transceiver, and yeah, then we could send out some data. That was not too hard to do, and so we said, okay, let's turn this into an end product, because yeah, this is a great idea. We can have the configurable digital stuff, the configurable analog stuff, and yeah, it would be nice to combine it with LoRaWAN.
Yes, the modern piece.
So yeah, that's why the journey started of making the module, and as easy as it was to send out just data over LoRaWAN, as harder it got while being in the development, and while having the certifications and FCC. I have a bit of experience with RF, but yeah, when you want to do everything very small and on real small scale, then RF will come and bite you. And yeah, that was quite a difficult task to make it really small. Okay, to make it really small, and so yeah, and then we came into weird situations that we had a shield, we needed a shield, so FCC demands a shield, and that the shield is actually going to work as an antenna. So that's just what you not want it to do. And so yeah, it took a long time. We expected it that there would be. Can we do a bit more quiet, because we got some comments. So that yeah, that was a problem, that we could not make it really small unless we did more our best, and yeah, we did finally, and we came through the certification of FCC, which was quite cumbersome, but we finally made it. It took us eventually over 2 years, and also yeah, we were really at front of the PSoC 6 development. So yeah, there was not a lot of tools available, and there were also yeah, a new tool which was a Modus Toolbox, but yeah, it wasn't really suited at that time to set up all the secure stuff, and yeah, we wanted to have a secure stack, so that was also a hard thing to do, the dual core debugging, etc. And also there was a PSoC Creator, and that couldn't really work with the dual core of PSoC 6. So we had to get going with Modus Toolbox, and yeah, that is where we made our first projects. And finally we said, okay, we are used to PSoC Creator, but we cannot use PSoC Creator, so we're going to make our own IDE. And so that, or our only IDE, we used Visual Studio Code, and we made our own setup over there, and that was quite cumbersome as well. But finally, it runs out of the box, and we have made a single click setup, so that yeah, that makes it all easy to install for people finally. So, and that's where we are now. We also made multiple example projects. Tomislav is going to show one, of course, with the Sprouty. We also have recently a Bluetooth BLE project where yeah, you can easily configure the LoRaWAN module over Bluetooth. Yeah, let's start with a workshop, the hands-on workshop. We are excited that we have again people who are joining, and if we are well, we have all the people has set up the initial code. Let's see, and let's hand over to Tomislav.
Hi, thank you, Rolf. Sorry, everyone, for a bit of a commotion before. It's absolutely true, Jack. There was a bit of a too much backlight, so I moved so you guys can get a better image of me. So let's get started with the workshop. I'm going to say this the last time. If you haven't already, visit our GitHub page. There you can find instructions to get going, to set up the Visual Studio Code and PSoC Creator. And if you have done that successfully, you should see the blue light blinking like this. If you have not, or if you have any questions during the presentation, you can always stop me, and I'll try to answer any question that you have. So let's start. Firstly, I'm going to share my screen. And I'm going to go on to GitHub. And here you can see the Sprouty workshop. And Sprouty workshop will consist of 3 parts. First part, we will implement the soil temperature, air temperature, and light intensity measurements, also with LEDs. And in the second part, we will implement the soil moisture measurement. And in the third part, we'll implement the LoRaWAN part. If you do not have a gateway for some reason, that's okay. You can still follow me during the first and second part and see the information about debugging. And then with the LoRaWAN part, you can just watch. But let's get going. Firstly, you should, as stated in the introduction, you should open your Visual Studio Code. As you probably already did, do a clean reconfigure. You'll need to select your programmer, and if you, because you got one programmer with the Sprouty, you will need to select this one. So CMSys, DAP, Applied Debugger. I have a different one. I have a Miniproc 4, so I will have the Infineon PSoC 3 programmer selected. Okay, and then you can build your project and you can launch it. And with the default Sprouty project, you should see a blue light blinking, and that's how you know you have everything correctly. You should also have went through the instruction of how to open a PSoC Creator. And in the PSoC Creator here, you will see a flashing LED, and it's done a bit differently. So if you take a look at the code, there is no actually code that flashes this LED. But it's all done here in, let's say, under the microcontroller itself. So there are 2 parts to PSoC. It's the upper part, which is the micro, and the lower part, which is kind of an FPGA. And you can use any hardware block, and you can connect it to any pin. And that's the huge advantage of PSoC, and therefore of Onethinx module. Right here, we have a clock connected to a D flip-flop, which reduces the speed a bit, the frequency, and it's outputted to a blue LED. And this blue LED flashes without any code written, and it will continue to flash like this. To start, we will go then to the GitHub page and press the part 1, start with part 1. Here we will start with temperature, so implementation and light implementation. And for that, we will need an analog to digital converter, because we read temperature from the NTCs, and we'll read light intensity from the photoresistors. And these are some analog values that we can read. So for this, we will need 3 analog inputs, and we will need 1 digital output to power these NTCs and this photoresistor. Why do we power the NTCs and photoresistors and not just constantly have them connected to 3.3 volts? Is to save power while they're sleeping. So if you put your device into sleep and it should consume low powers, these resistors should not be connected to voltage, so they do not consume any energy. So as I said before, 3 analog pins, 1 digital, and since we have an RGB LED, also we will need additional 3 digital outputs. So let's get started. So you have now opened PSoC Creator. We are in the top design here. You can double click top design, and we can delete the D flip-flop and the clock, and we can also delete this text. And what we will have here is a blue LED pin. Now there are several ways to take the pins and put them in this top design. So you can go and right here under ports and pins, and you can drag your digital output here. And this will set the pin up with the default setup from PSoC Creator. And you can double click it and then edit these values here. Or if you already have a pin set up, you can just copy it and paste it, and it will keep all the values there. So I will paste this several times since we need a digital output. But these digital outputs should not be connected internally. So they do not need to be connected to this schematic. So what I will do is actually before copying, I will edit this one and disable hardware connection. Hardware connection is like a connection to the inside, and it will just be digital output, which is controlled through software, through firmware. All the other things we can leave as is. So now we have a blue LED. We'll copy this and we'll paste it. We'll paste it several times until we get 4 digital outputs. And then we will change just the names of those outputs. So to match the name on the GitHub page, we will use, yes, S-Power, NTC Air, NTC Soil, and LSense. So SPWR. Yes, for digital outputs, we'll use LEDs, not analog names. So for this, we'll use LED G as green LED. And for this, we will use LED R as in red LED. So now we have 4 digital outputs. We also need to put in an analog block, an ADC block, and it on the right side, if you go under analog, ADC, you see a scanning ADC, and you click it, and you drag it out here. And we will also need 3 analog pins. Under ports and pins, you see analog pin, you click on it, you drag it, and you drag it here. We can drag additional 2 pins here, but it's not necessary, as we can modify 1 pin and then just copy it. So we'll say this is NTC Air. Everything else is okay. So we'll just copy it and paste it a few times and change the name. So this will be NTC Soil, and this will be LSense, if I'm not mistaken. So now we have 4 digital output pins, which are controlled by software, and we have 3 analog input pins, which are internally connected. So the checkbox, there's no checkbox for analog, but analogs are always internally connected. We have now modified all the pins internally as we wish. We now have to modify the ADC block. And you can go onto the Sprouty workshop, and here you can see how you can modify this ADC block. And so we will modify its name, a free run scan rate, and let's do that now. So we'll change its name to ADC. We'll change SPS to 1000. VREF select, we will change to VDDA. V negative for single-ended, we'll change to VSSA. We'll have the single-ended result format assigned. Let's increase for good measure samples average to 8. And we'll leave this as is. Averaging mode will be sequential fixed. And since we have 3 analog pins, we will need to increase this to 3. They are not differential, they are just single-ended, so we will change each to single-ended and make them averaged. This should have been everything. We also need to go into common and under sample mode select single shot. And again, all of this you can find on our GitHub page if you missed something, but I'll leave this up for a few seconds. So under common only there's single shot, and everything else is like this. So SPS 1000, VDDA, VSSA, signed, 8 samples average, sequential fixed, and all are single-ended and averaged. So we can now apply this, and we can connect these analog pins to the proper channels. And let's see on the GitHub page how are they actually connected. So we have soil to 0, air to 1. So soil to 0, and we have air to 1, and then that leaves us channel 2 for light sensing. And that is it. That is more or less the configuration for the first part of our workshop. Rolf?
Tomislav, I have a question. You did design that PCB for this, right?
I have, yes.
Yeah. Did you take into account the routing of the pins for the analog signals?
Yes. I took as much consideration as possible, but yeah, yes, I did.
Okay, but I mean, does it matter how you route it, or
yeah,
to which pin?
It actually does not matter. Like with other microcontrollers, it matters to which pin you connect your analog. How should I say, sensors or analog things to, let's say. And if you get the wrong one, you have to make another PCB, or if you're making a prototype, maybe scrape it a bit and solder it to another place. PSoC is wonderful because you do not need to worry about that. You can connect an analog functionality to any pin whatsoever, and that makes our module unique. That we are the only LoRaWAN module with this capability in hand. Thank you, Rolf.
Yeah, you're welcome.
So now let's just press Control S or file and then save. I already saved with Control S to save this. Now we have these pins here, but they are not actually connected to any of the external pins. So these are like virtual pins that are set up in the top design. And if you see on the left here under source, you will see something called pins. We will double click on this. which will open all the pins that we can connect these functionalities to. If we go back to our GitHub page, it will say you can see how these pins are routed. In the part 2, there will also be a part of a schematic where you can see on the schematic how it's routed. But later on, we'll also release the schematic and the design of the Sprouty, so you can see it yourself. So for red LED, this will be 12.5, and green is 12.4. So red is 12.5. And green is 12.4. I'm sure my team is carefully watching, so if I make a mistake, they can correct me. A blue LED is on 10.3. So blue LED is already on 10.3, as we already saw it blinking. So we know that's all right. We have LSense, so light sensing on 10.2. Then NTC air is on 10.1, and soil is 10.0. Air is on 10.1, soil is on 10.0. And I already got a message from my team. Let's see it. So LSense is, and we have S power, which is 11.5. Okay, thank you, team. Okay, now we should again save this with Control S or File, save, and now we can build the project. So we have everything configured. We have the top design, and we have connected this top design to actual pins of the microcontroller. So we can press build. And on the first go, it will take maybe a minute or two to build everything, but as we get along, it will get a bit faster.
You have a great voice for singing, Tommy.
Oh, thank you.
Thank you.
Thank you. I always had a soul for singing.
I know.
Yeah.
This is my waiting music.
You choose the wrong occupation.
Yeah, right. Okay, now that we have everything built, this creates some sort of API that you can use then in Visual Studio Code. We will not do the actual programming in PSoC Creator, but we use PSoC Creator for the setup. So if we now go back to Visual Studio Code, again, we see here there's no actual code linking the LED, but we saw it linking before magic, right? So now let's do a clean reconfigure, and we recommend you do this when you copy the project or when you do some modification in PSoC Creator and you build it. Okay, now we have the everything cleaned and configured, and first thing we need to do is since the LEDs are let's say always it's called common anode. Correct me, my team, if I'm wrong. LEDs are connected. It's on one LED, RGB LED with a common anode. It's always connected to the power. Yeah. And you actually turn the LED on by drawing the pin low to enable, let's say, the current flow. So we will actually turn off the LEDs by writing a 1 to them instead of 0.
What would also be a good practice is to use a define, for example, or an enum. Define LED on 0.
Yeah.
Define LED off 1.
Yeah. Maybe that's something we can introduce right now, although we didn't have this plan, but Rolf had this wonderful idea. So we will use a define. So it will use LED on. And as I said, we turn the LED on by writing 0. And we will do a define LED off as 1. Now you're also getting some free C programming instructions, and maybe you can use it in your next project. So right now what we'll do is we'll write to the pin. So we'll start by writing CY, GPIO, write, and we will use the same names as we used in the PSoC Creator. So as you know, we used LED or, let's start with RGB, so I don't forget an LED. So LED R underscore port, and this will give the port number, and then LED R num, this will give the number of the pin. And we want to turn it off, and instead of writing 1, we can write LED off, so we don't forget it's 1 for turning off. And this is for red LED. We'll do the same quickly for all the other LEDs. Maybe Ruud can now sing the waiting music.
Dum, dum, dum. So what you can see here is that the way you program the device is actually quite simple. Using the defines clarifies it a lot, especially if somebody else later needs to go through the code. So the remark of Rolf was very good.
Yeah.
You can also copy and paste. I just like to write.
Yeah, there's also auto completion, so that makes sense as well.
Yeah.
And, you will make less errors.
Yeah. So now all the LEDs should be off, and we can turn them on again by just copying this and writing LED on. Now let's start the ADC block. So we write ADC, and we use the same name for the block as we did in PSoC Creator. If we named it, for example, I love to drink lemonade, we'll start with I like to drink lemonade start. That's just a funny example everyone is cringing about here. Okay, so ADC starts, and now we have started the ADC block. We also need to define some variables, and we will use, as you can see also on our GitHub page, we will use int 16t, and we will use three variables, and let me stay the same as on our GitHub page. I'll use the same variable names, and of course you can just copy this code here and paste it in Visual Studio Code, and so you don't make any errors. So we have 3 variables. We have temperature air, temperature soil, and value light. So how will we use them? Firstly, and this is you can see this on our GitHub page, we need to turn on the power. As you saw earlier, we need to drive the output pin for power high. Then we'll have a 1 second delay just to wait for it to go high. We'll start the ADC conversion. We'll wait for the conversion to finish. We'll get the voltage from the channel 0, channel 1, okay, and channel 2, and then we'll turn off the sensors. Okay. So we have some questions about the PSoC Creator. Am I right, team? Okay. I understand some of you are not familiar with it. I'll go back to it. So PSoC Creator was a software used by Cypress. Cypress was how the company was called before Infineon purchased it. And they had this wonderful tool called PSoC Creator. Later, they what Cypress and now Infineon goes with is called Modus Toolbox. But unfortunately, Modus Toolbox does not have the ability yet to use UDBs. And what UDBs are some sort of universal blocks that you can connect to any pin, that you can do all wonderful stuff with. And PSoC Creator has those blocks. And that's why we stayed with PSoC Creator, but we also moved to Visual Studio Code because PSoC Creator does not support, let's say, the dual core functionality of our module where one core is locked. So we stayed with PSoC Creator because we saw it's a wonderful tool and you can do wonderful things with it. If not, you would need to use specified pins for specified functionality. But with PSoC Creator, when you draw the project and you build it, you can use it then in your code. And as we saw in the beginning, we had 0 code in Visual Studio Code, and the LED was blinking, and it's still blinking. It still has that same code where there is no actually blinking code in code. Okay, hopefully that clarified. If you have any specific question, my team can show me those specific questions. But let's continue.
Tomislav, maybe in PSoC Creator there is a little tab. You see on the right-hand side, you see all the components.
Yeah.
So these are the regular defined blocks, the CDBs, right?
SCBs.
SCBs, right.
Yeah.
So for the people that think, what is a UDB? Actually, they are the same as the devices here, but defined in sort of a file. If you go on the right, there's a little tab Onethinx on the screen of my colleague. And that is because he imported the UDBs in here. And in here, you can have some functions, as you see. So that means these functions you can load within the same drawing in here and define them with pins. So these are actually similar kind of devices.
Yeah. We can. What we can do is put a link in the comments to where it's explained how you can implement a UDB functionality like this into the PSoC 6, into the Onethinx module.
Yeah.
Yeah.
And maybe Rolf can explain also how he used UDBs to connect a lot of analog pins. Maybe some example on UDBs.
Yeah, I did so many stuff, mostly digital, but yeah, it's so easy. You can, if you don't have to watch out with the routing of your TCB. I mean, you can use any I/O to hook it up to a UART, for example. You can use any I/O to hook it up to SPI, I2C. It doesn't matter. So that makes your PCB layout really straightforward. And also, yeah, you can hook up like 15 UARTs if you like to have a some sort of device which which has many serial communications,
yeah,
or some sort of routing functions. But you can also decode like simple bit streams, encode or decode if you like. For example, what I did in the previous project was I had a 40-bit stream which was Manchester encoded. So a 0 is 0, 1, and a 1 is a or vice versa 1, 0. And you can detect that with on the edges with a timer, and then without any software you can clock all your pulse into a shift register, and then you just have to read it out. It's there for you, and you can build it, and you can also write it. So I wrote it in the schematic, so you can use all the OR blocks and XOR, etc. Timers. But you can also use Verilog if you are able to write in Verilog.
Yeah,
you
for
can
those
use Verilog.
For those that are hardcore, use Verilog. So
yeah, and then even you can put that in your own component. So you can make your own component with this functionality. And then also on top of that, you can also make your own configurator. So you can do a little C# coding, and then with a C# you can make the configuration view, let's say, and where you can do the configuration of that block.
So that's wonderful. So what he said, maybe to more layman, in a layman short way, is you can use all these special blocks, and you can make your own block from it, and it can do all complex things as you make it. And as Rolf here explained, he made a Manchester decoder with timer and some shift register, and made his own block from it. And this is without code.
Yeah. Also the way how the UARTs are in UDP blocks are done by Cypress and I2C. It's all made in Verilog, let's say. Yeah.
Okay. That's beautiful.
Yeah.
So let's continue with our use case. So we have 3 analog pins that we need to read, and as I said, we need to first enable the pin for power of those sensors. So we will write, and that is SPWR port.
To share your screen.
Oh, I'm no longer sharing my screen.
I think.
Okay. Let's share it once more. Okay, is that better? Yes, awesome, excellent. So as I was saying, we need to power on the S power pin for the sensors, and we do that similarly as we did to the LEDs. So S power num, and then we write 1 to it to power it. And then we need to do a short delay, so we will do a CY delay of 1. So we are sure it's on. Then we will start the ADC conversion. So we will write ADC start convert. And then we need to wait for the conversion to end. And we decided to use a blocking wait, so it waits until the conversion has finished. So again, we'll write ADC. It's always the same name as your blocking PSoC Creator. And we will write is end conversion, and we will give it what way we want to wait or not wait, and we will write cy sar wait wait for result, and this will block the code until the result has came back, and then we can actually read that result. And let's start with the first channel, and on the first channel we have temperature of the soil, and this is an ADC value that can be then converted to millivolts, but we also need to get the temperature somehow from it. And the easiest and the fastest way usually is to have an NTC table, and then we can give this NTC table a value, and it gives back a temperature. And this NTC table can be found in Sprouty.h. So if you double click it, you can see this table here, and it will return us a temperature. So we can write NTC table with open brackets as it is an array. We will get back the ADC get result 16, and we need to give it to the channel, and this is temperature soil is on the channel number 0, and we will do shift to the right by 3, and this is a way to read and get back the let's say more or less temperature, and this will give a resolution of 1 degrees Celsius. You can always go for more resolution. It will be a bit bigger table. But for this application, we think that this is more than enough. We'll repeat the same thing with temperature here. So EDC table, EDC get result 16, and the air temperature is of channel 1, and we will shift it by 3 places. And if you want to learn how to do this, you can Google NTC tables, and there is a bit more explanation of how this actually works. There was actually a bit more code behind this. It was not just shifting by 3, but since we only used a resolution of 1 Celsius, it was this was enough to achieve it. And thirdly, it's a light value for it. We don't need an NTC table because it's not temperature. It's just a light value, and we'll keep it in millivolts just so so we can understand it easier. And value light equals ADC counts to millivolts. To it, we need to give the channel of the light sensor, and that channel is 2. And we need to give the ADC result. So we'll write ADC get result 16, and again to it we need to give the channel. That's it on that. We will now just turn off the power of these sensors. So we'll write CY, GPIO, write, we'll use SPWR, port, SPWR, number, and we'll turn it off by writing 0 to it. And we'll press Control S to save it. In case you mess something up, or if you are unsure about anything, the code is here on our GitHub page, so you can always copy it. And hopefully I wrote everything right. In case I didn't, I will revert back to this code and see where I made some mistakes. So right now I have it saved. I will build the code. And you will see some errors disappear. And now the code has successfully built. And we see the Sprouty is still blinking, so we still have the old code on it. And when we program this code, we'll see all the LEDs turn off. And we'll put a breakpoint here, so we can actually stop the code, and we can see whether we have some good values. And what we should expect, since air temperature is about 24, maybe if I'm talking to it, there's some temperature there, so temperature increase. And we should see slightly higher temperature on the soil sensor, because I am holding it in my fingers, so we should expect about 28 degrees, maybe 30 degrees, maybe 32 degrees. We'll see. My hands are a bit warmer than last time. I'm already more confident this
More
time.
coffee. Yeah.
Yeah, and less coffee. Yeah.
Yeah.
So let's do build and launch. Okay, now we have it here. On the top right, you'll see some debugging buttons. You can press continue, step over, step into, step out to reset, stop, and things like that. And you can step over. So let's step over. But right now, I'm more interested in continuous, and so it continues until here, and we'll stop here, and I can read some values. So temperature soil is 34. So yeah, my hands are quite a bit warmer than 28 a few days ago. Air temperature is 25, and the value light is so 680 millivolts. If I will now release my finger from the soil temperature, I will put my finger on the air temperature if I can, and I will put my finger over the light sensor. So we should see the light sensor value decrease. I doubt the soil temperature will decrease as quickly, but we should see a slight increase in the air temperature. I cannot put my finger fully on the air temperature sensor, but hopefully we see some difference from 32, 25, and 680. We press play, we see 28, which is lower since I moved my finger away. This is 30 because I put my finger besides it, and the value light is a bit lower, around 450. And this demonstrates the part 1 of our workshop, where we implemented the LEDs, we implemented the soil temperature sensing, air temperature sensing, and light sensing. Ruud has something to add.
Well, I mean, I'm trying to be useful as well today. So on the left side, you also see this little tab called Watch. Now, it can be very handy if you're debugging software to put some of those variables like temp, soil, or whatever you see over here, how my colleague is doing, add to Watch. It actually gives the real value that it has since the run. So every time you press run again, or the green continue arrow, you will see the value changing in the left pane, and that can be very useful if you're debugging.
Thank you, Ruud. Absolutely right. You're very valuable, and good to point out this. I've used Watch many times.
Yeah, me as well.
It helps you a lot. So yes, Visual Studio Code because of it is very great. So once again, in Watch we see value light of 1100, 1200. If I put my finger over it and press play, we see very low value. If I remove finger, higher value, put finger, lower value. This is why Watch is very handy. Okay, this concludes part 1 of the workshop. We'll now move on to part 2. Again, if you didn't manage to do some parts, you can always go onto our GitHub page, and you can copy the code and follow the instructions for the PSoC Creator. So let's move to part number 2. And in part number 2, we'll talk about soil moisture. And the way we implemented the soil moisture was we made some traces here on the PCB, and we connected those traces to some internal functionalities of the PSoC. So you might imagine, like if you see this image on our GitHub page, that we use some sort of external oscillator or an operational amplifier, comparator, and things like that. But no, we only used resistors because we utilized the internal block of the PSoC in the PSoC Creator, operational amplifier, internal block, which was a comparator and a counter. And you will see those blocks a little below when we start with them. So at first we use these PCB traces as, let's say, we use them as a capacitor, let's say. So when there was no water around it, there was one capacitance, based on the amount of water there is around it, the capacitance of the capacitor changes. And during this presentation, I'll use my hands as water, because if I put my hands around it, the capacitance changes as if there was water around it. So there's an oscillator that oscillates based on the capacitance of this capacitor. And its output frequency is directly connected to the capacitance of the capacitor. So when the capacitance changes, also the frequency changes. And how do we count this? Well, there is a great internal block in PSoC Creator and PSoC called counter, but it counts digital signals, and we can adjust output a frequency to it and let it count. So we use a low power comparator in between. This low power comparator compares this analog value on the input to a certain reference value, and then outputs a digital signal on its output, more or less digital signal. By measuring in a fixed time, by measuring these signals, we can get, let's say, we can read more or less the frequency of the output, and by that determine whether there is a lot of water or no water around Sprouty. So, as I already mentioned, for this we will need an op-amp, and wonderful thing about PSoC, it has an internal op-amp. We'll need a low power comparator, a reference voltage, a timer counter block, a clock, and 3 analog pins. On the right here, we added a little image where you can see where all these blocks are located, because sometimes it can be a bit difficult to find them. Also, what you can do is, you will see in PSoC Creator, there is a search bar here, and you can write, for example, op-amp, and it will just show you where the op-amp is. So let's drag these blocks. So as I said, we will need, we'll go to Cypress here on the right. We'll need 3 analog pins. We'll need an op-amp. We will need a comparator, which is actually a low power comparator. We will need a reference voltage for it. We will need a timer counter block. And we will need a clock for it. And I'm doing this pretty fast, so always you can go back to the GitHub page and see, but I'll just leave this here for 30 seconds, so in case you need it, you can still see it.
So you can also imagine that in the normal situation where you use the normal Atmega controller, you need to get an op-amp on your board. You need to get a comparator. This is all included in the PSoC chip itself. So this is awesome. It saves you hardware.
Right, and it's not part of the code. It works without the actual code.
Exactly, and yeah.
It's like to program it in Verilog, but it was very simple just by dragging and dropping here.
Yeah.
So now let's connect these, and then let's modify them. We'll need 1 pin for plus, 1 pin for minus. We'll also need 1 pin for output, and we'll connect this using the wire tool on the left here, or by pressing on the keyboard W. So wire tool here, wire tool there, and we will have it. We'll move this a bit so you can see it a bit easier. And I've already done it so many times that okay. So let's modify things. Let's start on the left with plus. So we'll name this OA as an operational amplifier plus. And it's the same as on our GitHub page. We'll name this OA minus. We will name pin 3 here, we'll name it OA out as the output of the operational amplifier. We'll name this just LP comp. And we'll modify it now as well. And we'll also name this the counter. And we'll modify it a bit to add another pin here. So, and yes, I didn't modify the op-amp. Thank you, team. So let's see how we modify the op-amp. So let's go on our GitHub page. We got 3 analog pins, 1, 1, 1. Those are all analog pins. Here we see how they are connected. Here we can see the simple datasheet that I mentioned before. This is not an actual operational amplifier. These are just output pins of the Onethinx module from PSoC Creator. We'll upload all the files later for you. You can expect them next week on our GitHub page, where you can explore Sprouty schematic in more depth. So let's see. Op amp. The mode is op amp. We need to change output drive output to pin, and the rest is the same, I presume. So this goes output to a pin. We'll apply it and press OK. So change its name to op amp and output to a pin. Next we have this band gap reference, which is OK already, it's on default. We have this low power comparator, which we just deleted, which we just named it LPCOM. And let's see on our GitHub page how it looks like. So hysteresis is enabled. It's a direct output configuration, normal, power, and fast. So enable direct normal power. So we'll change this to normal power. Rising edge, and walkover ref is not turned on. So yes, this is the same as on our GitHub page. We click apply to save it, and then we press OK. Then we'll modify this clock. We'll modify it to 8 megahertz, and then you can press OK, and it saves. Okay. The clock is auto-enabled, so we don't need to change its name and enable it. It will be automatically enabled. Then we move to this timer counter block. We named that T counter. So let's see what we need to change there. It will be 32 bits. The white by one continues. 32 bits. The white by one continues. It counts up. Period, I already know from my GitHub page, is a bit higher. It's 4 million. We'll never get 4 million. That's about 4 megahertz. The maximum we'll get is about 90-100 kilohertz. But just to give us some room, let's see on our GitHub page the other ports. So capture input disabled, interrupt source none. Okay. And we'll have on inputs, we will have a count input, and we will enable this on rising edge. So we will count whatever we get from the low power comparator by its rising edge. Again, you can go on our GitHub page for all the settings. We'll press apply and OK. And now we got this count pin here, and we just connect these by the wire to it. And if it looks like this, you can move it a bit up to make it a bit more beautiful. Now that we have defined this is, I press Control S to save. Then we, these are still virtual pins that are not actually connected to the outside. We need to connect them outside again with these pins here on the left, and we already have them open here. But if you don't have them open, we can double click pins. Now we have these 3 pins which we need to connect to the outside, and let's see on our GitHub page how we connected them. So plus all of them are on port 9. So I'll just remember that plus is 0, minus is 1, and out is 2. So plus, minus, out. So plus is 0. Minus is 1, and out is 2. Okay, now that we have that set up, you can go and click File, Save, or Control S, and now we have everything set up, and now we can build it again. And again, you can use this build here, or you can go to build on the top and do build 1 to 3, or press Shift F6. And once we build this, we will hopefully not need to use PSoC Creator again for this project, but we will have everything set up. In the next part, in part 3, in LoRaWAN, we will not be using PSoC Creator at all. It will all be done in Visual Studio Code. wants to sing the wait music next? Once that will build, then we'll do again a clean reconfigure in Visual Studio Code. Now that we move to Visual Studio Code, we can stop debugging, and we will do a clean reconfigure here, and then we will continue with our programming. Okay, now that that is clean built, I will just use my second screen as a reference to show you how we should program it. So we'll add another variable. It will be a unsigned integer of 32 bits, and we'll call it count. And here we will say the actual count from the timer counter. We need to also start these blocks. So we know we have an op-amp, and we'll use the same name. We'll use op-amp start. We'll use lp-com start, and we'll use the counter start. And now we have started or enabled these blocks for use. Next thing we will do is we will go to the end of the where we finished previously, and we can add the code for counting the frequency. And firstly, what we will do is we will set the counter, the actual counter block, to 0, so we know it starts actually from 0 or not from any other number. So we'll go to counter, set counter, and we'll set the 0. Next thing we need to do is we need to trigger the actual start of the counter, and we'll write the counter start. And to measure the frequency, we'll wait for 1 second, and then we will see how many counts in 1 second we got, and that will get us frequency. Of course, we could reduce this number. We could write 100 milliseconds, 10 milliseconds. It will give us a different reading, but then we need to multiply by the difference to 1 to see the actual frequency. So if we use 10 milliseconds, for example, of wait time, we will multiply it by 100, because 1 second has 100 times 10 milliseconds, and then we'll get the actual frequency. But in this case, we'll just use a CY delay of 1, so it's easier to understand, and after that, we will get the exact frequency in hertz of the frequency signal that we have on the input. Then what we will need to do is capture this count. So we'll write the counter. We'll write the counter trigger capture. And it needs some time to save it in the actual register. So we'll wait for 1 second for it to save. And the variable that we made called count, we'll use that now. So count equals the counter get capture. So it gets the value from the register. And then what we need to do is we need to do a reload after that. Okay, and that should be it with this. We should be able to count the frequency on the input. Let's now move this breakpoint here. And what we can also do, we can also add this count to the watch as well. So when we build it and then build and launch it, it will be displayed on the left here. So we're building it now, it's successfully built, and then we can press build and launch to program it and debug it actually. Thank you. So now that it's debugging, we can press play or press continue, and it will stop at this breakpoint, and we'll see some value of count, hopefully. So now we see about 83 kilohertz, so 83,000 hertz, 83,013. And that's where I'm not holding it in any special way. If so, that means it's dry. When I put my hand around it and we press continue, I should see a lower number, and a lower number in this case will mean more humid. So we got about 24 kilohertz. If I put it in my water here, I will drink it before, not after. We should get an even lower value than 24 kilohertz. So when I press play, we get a value of 8 kilohertz, and this is because it's more wet. And if I take it out now, I can dry it a bit. I'll use my beautiful t-shirt. And now, if I press continue again, we'll see a slightly higher value, actually a lot higher value. It's about 65 kilohertz. If I press again, yeah, it's 82 as I move my fingers away from the actual capacitor, from the traces. And that's more or less finished for part 2. Now what we have did is we used Onethinx module to measure soil temperature, to measure air temperature and light value using analog pins. And then we used some special functionality of PSoC to, let's say, measure the changes of capacitance of the traces in order to measure how much water or humidity there is around the sensor. And as Rolf and Ruud have mentioned before, this was all done by using the internal blocks. We only used resistors for this functionality. We didn't use any op-amps, we didn't use any comparators or anything similar, just resistors connected to the Onethinx module, and the traces itself are the PCB traces. So only resistors and a Onethinx module. Now that we have finished that, we can stop. Thank you. Now I have 2 waters. Now I must have mixed them. Thank you, Edwin. I have a new helper here. Yesterday it was Carlo, but now I have Edwin. So we can stop debugging now, and we can go on to step 3. Do we have any questions maybe that we can answer before we go on to the next segment? Or
I did not see any questions coming in.
That's awesome. That means I did a very good job.
I'm sure you do a great job.
Oh, thank you.
It's just a question if on the other side the job is also done correctly.
True.
Anybody any questions on the devices or the programming or on the syntax, or please let us know. We're open to that. So what I also want to emphasize is that, just as Tomislav said, you don't need a lot. There's a lot of devices that you can buy that do LoRa, but not a lot of them have the capability of integrating your own code inside of the same device. So in this case, we use the CM0 core for the LoRa stack, and the CM4 core in the module is completely yours to program, which makes it very nice to use. That's why I use it a lot as well.
Thank you, Ruud. So let's continue to part 3 now. So let's go on GitHub and let's click on part 3. As I mentioned before, we will not need PSoC Creator, as we already did all the sensor measurements and all the setup there. Now we'll use only Visual Studio Code. Maybe Rolf can jump in and explain a bit more about this configurations, how we configure the LoRaWAN stack, how we configure structures for it, and structure for sleep as well, as he is the one that created it. So Rolf,
correct. Okay. Let me see if I have the right source code in front of me. Yes, I have. So I will share my screen so the participants can follow along. Let's see if I can manage to do that. Second. Oh. I'm gonna walk with your.
Yeah, maybe I can
screen,
show it and you tell it.
So yeah, this is a bit better. Oh, that's okay. Yeah, so we have a structure for the configuration of LoRaWAN, and that means we kept all configurable settings in one place, and that makes it easy if you want to send your configuration data over. So you just have one block of data with all the configuration there. And you also can easily use a pointer to this block inside the LoRaWAN init call to have all the settings implemented. And we have several settings. So first, of course, we have the keys, which we need to be which needs to be referenced, and that's in a separate file. Can you show?
Yes, of course.
So the keys are inside. Let's see, in this case, because it doesn't have to be the same, LoRaWAN_keys.h. There are the files, but you can, of course, put them anywhere you like, as long as you reference them well. These are the keys which are implemented for LoRaWAN. As you see over here, there's a fixed def UI. So the def UI is filled in the field. You can also use this def UI and then within two brackets at the left and the right. And then it will take the internal def UI, and that's unique over all the Onethinx modules. So we bought an IEEE range, and all our devices come with a unique def UI. So that's what you can use. You can also use your own if you like. Then we have app UI, UI or join UI for LoRa 1.0 or 1.4, and also the app key, so that yeah.
Don't copy this.
Okay, then you have a problem with your device.
Yeah.
Okay.
The right is only for this example. For the next one, I'll use a different one. So.
Okay. Anyway, so that's that are the keys which you should fill in. Next to we have a join data rate. So this means you can join on a different data rate than you want to do the eventually sending of the data. So you can use the automatic data rate adaptation, which tries on different frequencies, different data rates, and Tomislav set it to power max, so that means it will try to join with maximum power. You can also set it to power auto. I guess I'm not sure about this.
No, I don't think so.
No. This was correct. So I wouldn't advise to use power max in a situation where you have your gateway next to you, because yeah, it's not needed, and you can also interfere others. So best is to keep it low, to keep it low for testing if you have your gateway nearby.
Saves power.
Saves power as well if you use an antenna. Then you can, when you start joining, the system will try several times to join. You can put in an amount that you want the system to try to join. In this case, it's 5, which should be really sufficient if you have your gateway next to you. It will probably join on the first join request. And there we have the subbands, so 2 subbands for the US. You can put different subbands, and that means 8 channels which you can configure. And for the EU version, we have 8 default subbands, which are implemented in the 1.02 version. Then TX confirmed, so we can change the structure. We can change it on the fly. So while in your LoRaWAN loop, you can change TX confirmed from true to false. So in the setting, I would advise to keep it to false, because you don't want to send every time a confirm message. And but whenever you want to, you can set it to true. Then the TX data rate. So if you want to use ADR, and that's especially for applications where you have a static location or a fixed location, you use ADR, because then the gateway will tell you which power you should use and which data rate you should use. And when you are in a moving situation, so for example on a car, you cannot use this, because the power you need doesn't probably match with what the gateway sees, because you're probably moved much further, and then you need more power. So for a fixed location, I would use ADR, but not for mobile applications. TX port or F port, that's the port which is usually one for LoRa. So I would advise to use just port 1 unless you have a special application. But okay, RX Boost, the SX1262 has a boost mode for RX. That means you can increase your boost your RX signal by a booster which consumes additional power, but yeah, it makes you it gives a few dBs gain in your RX signal. So you might want to use it if you're far away from your gateway, and if you want to have if you want to get the downlink messages well. Then we have some settings for system idle. That means that the M0, the radio stack, does his thing, and while not doing anything, you can put it in different modes. So you can put it in sleep, you can put it in deep sleep, which is recommended, because why not? But you can also keep it active if you don't like the switching. But yeah, generally we keep it in deep sleep. We have a Bluetooth external crystal oscillator, and if you want to use Bluetooth, you want to leave it on when the M0 is idling. So yeah, that's a 32 megahertz crystal, which is used by the Bluetooth. Then we have the debug on. That means when the system goes in idle, you want, if you want to keep debugging, then you set it to true, because otherwise your debug port will be kicked out, and it saves some power, but yeah, you cannot debug anymore. Then additionally, we have a function called LoRaWAN sleep, and then the LoRaWAN modules goes into sleep. You can select different modes. You can select hibernate, you can select sleep, and you can select deep sleep. Yeah, of course, hibernate is the most power effective way to go in, yeah, kind of sleep, to wait and save power. But you can also go in deep sleep or sleep. Deep sleep or sleep are virtually the same. On the background, it is possible with deep sleep that you select memory regions which you can unpower. So you could save in that mode. You could save some additional power, but we didn't implement it because it's not up to us, and we just maintain all the RAM active, and that means that we have, I guess 1.5 microamp somewhere
Yeah.
in deep sleep. In hibernate, it's yeah, like nanos, 300 nanoamp.
So is the RAM retained in hibernate or?
No, in hibernate the RAM isn't retained, although there are 16 registers which you can use. The backup registers, which you have 30 bits registers which you can use to save some data. For example, the reason why you went into hibernate or yeah, whatever. Also, the RTC clock is in the feedback-up space. That means that this also keeps powered, and it keeps, if you have it activated, it keeps doing this job. So the time will keep running. And also, I've had several applications where we replaced the LoRa radio with our module, and also kicked out the custom RTC clock, because you can use this one in the module. So and that's makes it, we implemented the API, and that makes it easy to use, for example, a wake-up time. So when you have the RTC running, you can set up any time that you want to wake up. You can set the time with a LoRa set time. You can read the time, a LoRa and read time for read timestamp. And you can also set a specific time that you want to go and sleep. Other than that, you can also wake up by a external pin, and that's called the wake up pin. That's on P0.4, and anything you hook up to that pin, you can set it to wake up when going high or wake up when going low. It will wake up the MCU, and then you can continue your code. And it's really easy to use, because it's just one API call with this structure which you give along, and then it goes into sleep as long as you will. You don't have to really bother about setting up all the configurability, all the configurations for the wake up, because a lot of is being done. Some things which should be user depending is which IOs you should want to configure in what state, because that's something the radio stack, you don't want to let that over to the radio stack. You have your own, you know what you should set on IO, but all the rest, like oscillators, digital blocks, analog stuff, it's all done on the M0 core. So you really don't have to bother much to put it to sleep. And unlike other CPUs, where you have to really watch close what you set to make it to go to sleep, this is fairly easy. So that's it about these two configuration structures, and we keep them set in a structure, so you can easily send them over. For example, if you use Bluetooth, you can just copy all the data in a block and copy to the, for example, sleep configuration, and then you can set a different sleep using a BLE, or you can set different configuration for the LoRaWAN. You can send it over by Bluetooth, for example, and then replace the complete block, if you like. So that's it, Tomislav.
Thank you. Thank you, Rolf.
Any more suggestions which I could
no, I think
elaborate on?
That's it for today. If you want to jump in, you can always jump in. Thank you for the detailed explanation, Rolf. Guys, Rolf is the Brian, creator of this module, and if anyone knows anything about this module, it's him. So thank you all for the detailed explanation. So let's continue with Visual Studio Code. Where we stopped off was we read all the data from the sensors, and now we want to save them in a new array so it can be easily sent to the LoRaWAN network. And firstly, also when we call the LoRaWAN functions, those functions return some values, and they return them in a structure of sorts. And then you can use that structure for debugging or checking whether your sensor or your device is connected to the network and similar. So we'll write core status underscore t as core status. And then just below here, we'll write, we'll make an array of unsigned integer of 8 bits. And we'll call it data, and it will be of length 4. So now we have all the variables that we need. Again, you can use GitHub to check it, and then we'll move down. Now we want to create, we want to save data in this array, and since we have 4 elements of 8 bits, we'll set it up in this way. So we'll use data and first byte of 0. In it, we will save the counts from the frequency counter from the counter that we made previously. And we'll use that by dividing it by 1000, since we don't really need the precision of, let's say, each hertz, but we can say, as you already saw, if there's a lot of water, it's about 8 kilohertz. If there is no water, it's about 90 kilohertz. And that gives us enough resolution. Of course, we could have used a structure where we could pack this data even more closely together and compress it a bit more. But just for simplicity of our users, we decided to make an array. Next, we'll save this. We'll save soil temperature and air temperature. So we'll use data, and the second element, which is 1, equals temperature soil, I believe, if I'm not mistaken.
Yeah.
Okay. It's the second one, right? Yes. So we'll use temperature soil, and we'll add 40 to it. Why do we add 40 to it? Let's say the minimum value that we'll measure is -40, although we'll never get there, but just for safety. So in UINT 8 we don't go negative, and let's say we want to save a bit of space, and we added +40 to it. So when we calculate the actual value, we'll write -40. So if we get a value of, let's say, 25, we'll save it as 65, and then we'll do -40 on that. Data 2 equals temperature air plus 40, and data 3, which is the 4th element, equals value light. And since that value is a bit big, we'll divide it by 20 to save it. We'll use some resolution, but we can lose some resolution to save it in UINT 8. And next thing we need to do is we need to send this data. So we'll write LoRaWAN send, and we will give it the array which we wish to send. We'll give the length of this array. And I forgot some things, but I'll get back to that right now. And we give it the wait mode that we want to wait in. And as Rolf explained, there are different wait modes, but we'll use M4 wait in deep sleep. What I forgot is I actually forgot to init the stack, and I actually forgot to join the network. So I cannot send anything without joining the network. So I will do here a LoRaWAN init, and I will give it the core configuration structure that we made before, and that Rolf so kindly explained to you what it is. Then we will do a LoRaWAN join. This will join the network, and again we will give it what kind of how we want to wait, and we want to wait in deep sleep. And for now, we will check whether it has joined the network, and to check whether it joined the network, we will just join function, and all functions returns some sort of values in a structure, and this is in core. We save in core structure that we made previously, and I wrote it wrong, so it's more struct. And just if you want to debug your code, it's good to place it everywhere where there is a LoRaWAN call. Then after the function has finished, you can check all the variables inside that structure.
Also, what also is nice, if you want to know more about the core structure, core status structure, you can click on it and do a right click, and then you get to the structures type. So if you go on the core status, right click, and then go to definition, then you find the definition, and then you can go into core status, right? That went quick, but I hope everyone's seen it. Then you get to the core status type, and over there you see that the core status consists of a few variables, and one of the first one variable is the parameters, and that means the parameters which you give along with the call. So the status tells something about if your parameters are right. So you can go into that. It doesn't do much, but you can only read the status of the parameters, and then you can see if the parameters which you gave along are okay, and it will return that function with the status. Also, for LoRaWAN functions, you have a radio status, so that tells the status of the radio of the SX1262, and there you can see if it's configured already, and if the radio is busy. So if the radio is sending data or in receiving mode, you can read this bit to see what's going on. Then you have the MAC layer. So the MAC layer is on top of the radio, and there you can see the different statuses of the aspects of the MAC layer. For example, if the radio received a confirmed downlink, or if you just got any messages, if the LoRa network is joined, if it's busy, etc. You can read the part which you received your packet on, but also you can, if the MAC commands it, the amount of gateways which you received the data on, and that can also get into RSSI if you want. There's more than that, but it's just a quick show of what's possible. Let's see, back to down. Also,
system.
Also the system. So the systems tell something about what tech version is running on the background. Also, if you like, if it's busy, if the system is busy, and also the errors are there. So it's generally a structure is with all the data which comes back from the stack. And if you have run into any problems, let's say that you do not join, I suggest read that status. Then it tells more what's going on the background.
Yeah, and just to hop into the same subject, again, the watch, if you enter core status in the watch list, you can have a little tree view kind of where you can walk through and see the status as soon as you enter your breakpoint.
Yeah, let's do that.
Yeah.
It's nice, and you can see
Yeah.
it's joined, it's not joined, radio signal.
Right. So let's continue, and let's do that when we will be actually debugging. So let's see right now. After a join, as Rolf already explained, a bit of a structure. If you go core status.mac.isJoin, that will be either true or false where it joined. In this case, if it's true, we don't want it to stop. We want it to continue forward. But if it's not joined, then we want to do something. Then what we will do, and this is just for this example, we'll turn on the red LED and we'll wait in while loop, since you are debugging here, and then you can stop it, and if it doesn't connect the network, so it doesn't use barrier or anything. But later on in your project, you can implement some sort of sleep, or that the user presses the button again when it believes it will join the network. So there you can do your own thing. So right now we will just turn on the red LED, and we can do that by copying this line, pasting it here, and writing LED on, and below it will make an infinite while. Nope.
Put it into hibernate.
Or you can put it into hibernate.
It will save some battery. Probably it's a battery operated device.
True. So that you can investigate on later. For now, we'll just put it in a while loop, and you can see in red LED, and when it's red, it's bad. So yes, we can go forward, and now that we have created this data array, we have sent it, we can put the whole device into sleep. And this is not just LoRaWAN, but it's the whole device by calling LoRaWAN sleep and giving it the structure where we defined all the sleep parameters before. This was the core. Nope. How is it called? Sleep config. And this will basically put the device in sleep based on the parameters that you gave, and you can change those parameters on the fly. So you could before here just say sleep config dot, for example, sleep cores, and we'll change this and change the wake up pin, or change anything. And of course you can change the things about the stack on the fly as well. So before sending, if you for example wanted to, you have different situations, you could change core config, you could say dx f port, and you can change the f port to here, and then it will send on f port 2, and you do not need to do a LoRaWAN init again. You can do it on the fly. Okay, and that's more or less it. What I think I did on the examples online, just additionally, I turned on the green LED while reading the sensors, and so I turn it on in the beginning, and I turn the green LED off just before sending the data, and it's already off, and that's it. Since we didn't do any configuration in the PSoC Creator, we don't need to do a clean reconfigure. We can just try it by building, and then building and launching, and hopefully we'll see something more. I set up my keys here. If you didn't set up your keys, if you don't have them, that's okay. You can just follow along. But as we already explained earlier, this is where you set up your keys in the LoRaWAN keys. This will connect to a TTN network. That's here, a public network that we have in our company factory, and then online we'll see this data, and you'll see that I actually added a parser on it, on that device, that actually parses this data that we modified and gives us some values at the output. So let's build and launch.
You can meanwhile go into GDB server and see what's going on, if you like. At the right. Yeah. There you can see the actual programming taking place. And also you can, if you scroll up, you can see the dev UI of the device itself. So if you go a bit below, there you are. That's the dev UI device,
of the module. Yes.
of the module. Yeah.
Okay. As I said already, so let's put a breakpoint here just before join, and let's see in the init. Let's put this core status in the watch as root explained. So if we continue now, when it goes through init, we can go on the left on the watch here, and we can press this arrow and check where everything is okay. So we see the parameters are okay, the radio is okay, it's configured, it's not busy. You can see Mac is currently okay. It's not joined. After join, we'll hopefully see that it is joined, and you can see a lot of parameters and system parameters as well. You can set the battery level if you have a battery operated device. It started, is busy, sleeping, all these parameters you can see here. So now if we step over, it will join the network. Okay, now it has joined the network, it has stepped over, and we can either go on the left here under Mac, under is join has changed to true. We can see it's a public network, and also we can hover over here and see that this is true. It has joined the network and it will not step into this. So let's close this watch, and let's go until send. Okay, now we see that all the data is on the left. We have a count about 48 kilohertz, and that's just because I have my fingers around it a bit. We have a light of 900, we have air temperature of 25, and soil temperature about 28 because I was holding my finger on the sensor. We can now go to TTN, and Rock, if you can zoom in on me just so I can log in my TTN without everyone seeing that I'm logging into TTN. We will log into TTN and show you the actual data that's being received by the network. Thank you, Rock. This will only take a moment. I'm already logged in, and I have the devices ready, and I can see already on it that it's receiving data.
I cannot see your screen.
Yeah, and Rock can now continue with the screen share. Okay. Now that it has joined the network, I have stopped and used the code here before sending. I will remove this breakpoint and I will let it continue. It will wake up, I believe, every 1 minute. And here it has sent some data. These are hex values, and you can see here, because we divided the light value by 20, we lose some resolution, but the light value is 900 here. Soil moisture is 48 kilohertz because I'm holding my finger around it. Air temperature is 25, and soil temperature, as we saw, is 28, as we saw before. And now if I press the button on Sprouty, it should send again, and I should have held my hand around it, and we should be getting some different values. You cannot send too quickly. There are duty cycle limitations that Onethinx module implements, and of course, for when you are just debugging your application, maybe it's okay to send more often, but we do not recommend it. And in your end application, if there are problems, there may be problems because of duty cycle. So let's see another. Okay, now I have pressed it. Soil moisture changed a bit. I put my fingers a bit more around it, and soil temperature increased to 36 because I was holding my fingers onto it. If I hold my finger over the light sensor, we should see the light value go even more down. I have now pressed the button and it went down to 380, and soil moisture went to 84 because I was not holding my hand over the capacitive area here. maybe we can. Is the coffee already cold? I guess the coffee is already cold, and there is no coffee temperature measurement today. But if you check out our stream from a few days ago, you will see me measuring the temperature of my coffee, which I had too much of that day. Today I will sleep happily, knowing this all went well. But on Tuesday I could not sleep because they gave me too much coffee. Sure. Let's check what's the temperature of this coffee. Okay.
Yeah.
Thank you.
You're welcome.
Let's see if it's already at room temperature or not. So I put Sprouty inside. Yeah, the coffee is a bit warm. I can already feel it's warmed, and I can press the button or wait a minute, and we'll see what's the temperature of coffee. Okay, we see the temperature of coffee is 50 degrees Celsius, as you can see right here. So temperature soil is 50, and moisture is 11 because it's fully inserted into the coffee.
It's light coffee.
Yeah, it's
very light, very light.
Yeah, very light.
It's got sweeteners instead of sugar, right?
Yeah, of course. Maybe we can do even more measurements of coffee with Sprouty, but I wouldn't recommend drinking this coffee afterwards. It has been touched by the PCB. That's it, folks. I hope you enjoyed our little presentation, our workshop, and that's it from me. I give the word to our host Anita, and let's wrap this.
Thank you, Tom, for this amazing presentation, for the workshop. I'm sure people learned a lot. We also have a question from Sujit Anandan. Which gateway are you using with Sprouty now in the workshop?
Yes, thank you. Right now we are using the MikroTik gateway, the LR8. We're not sponsoring any gateways right now or anything like that, but we found that MikroTik did the best of all the gateways. It was easier to set up, so we are using that. You can go on our forum, look for gateways that we tested with our module, and just any LoRaWAN gateways is okay. Then again, we should mention, as we are getting many customer service requests, you cannot use our module as a gateway. Our module cannot be a gateway. Not that our module cannot be a gateway. You cannot use any LoRaWAN module as a gateway. For gateways, there are special chips that you need to use. You can use our module for LoRa to LoRa communication, which is not LoRaWAN, but just a physical LoRa communication. And if you have more questions about that, you can contact us on info@onethinx.com.
Shout out to Ted McAllister, who said great session, Tom.
Hey, thank you, Ted. Yeah.
Ted, if you can hear us, you can also text. And also Yak, thanks for the workshop, nice improvements. Thank you, Yak. I hope I pronounced well. And then we have another question. Yak, does the module implement EU 915 as well?
Maybe Rolf can answer that.
Unfortunately not. Currently, we have the US module, and which supports the frequency bands, but we currently haven't had a use case where we need the EU 915. But simply because it takes time to implement, and if we have a nice use case with a good volume, then for sure we will implement it. But yeah, as long as no one needs it, we don't gonna make it, because it's really a lot of work, and we also have to do the LoRa Alliance certification for that, and that's quite cumbersome if you have a customer who only wants to try. That's it.
Yeah, so if you have an application that's really special and it's enough volume, we're definitely willing to go that route. And maybe if you do, it's an idea to organize a meeting before with us, and let's talk about it.
Thank you, Rolf and Tom. Also, another question from Jack. Which LoRaWAN specification version has been implemented in 1.0 and which regional settings?
Okay, so yeah, okay. We have implemented the 1.02, and we have worked on 1.04, and we have it up and running. We have done the tests, only we don't have released it yet. Yeah, we need to release it. It has additional improvements, not very much, but some improvements with some settings, and yeah, makes it a bit better. But we don't have to release it. We have it internally right for testing. So it will be, yeah, probably released somewhere this year.
Thank you, Rolf. If there is any other question, please just put it in the chat. Otherwise, this is.
I believe from Jack there's. Oh yes, Ruud, you already answered. Yeah. So Jack, question: what type of coins cell to use with Sprouty?
Yeah, that's also a good one. The problem is with most just normal coin cells is that they are not suited for LoRaWAN. So you cannot draw any more current than like 10 milliamps maximum. So that will drain battery, and you have also a high internal impedance. So like a few hundred ohms, and then your voltage will drop, and that won't work. You can test a CR, say your CR2450, when you set the TX power to really a low output power, so 28 dBm accumulation. Then you can use it for testing. But for any more higher power, I wouldn't use the CR version, and therefore we recommend a LIR R2450, which is a rechargeable one, which has a much lower impedance and can deliver much more milliamps.
We saw good things with the lithium primary batteries that we use or that our clients use in their projects. There are some problems with it, but overall they are non-rechargeable batteries and they can last for really long. But as Rolf, our CTO, found out, they still, while you can draw low currents for it, you should not do it for a long time, because there is a layer that
correct,
that
it's
changes
called passivation, passivation layer, and that builds up internally, and that's in fact that's a good thing, because it protects the battery from self-discharge. So that's why they last so long. But if this layer grows too wide, let's say, then the internal resistance get even higher, builds up, and it breaks down when you draw some current. So
so it may need an initial high current draw to break it out of those.
Yeah, sometimes you need to send data just to break it, and some might say, okay, I use a bigger battery, so it might last longer, but that's not the case, because for a bigger battery,
it makes a bigger layer which is harder to break.
Yeah. Like the 30 milliamp is not enough to break this layer. Then you can better use a smaller battery, like a AA type of battery, which with LoRaWAN 7 you break some of the passivation. Yeah.
And we had some cases, for example, in agriculture, where we used lithium primary battery, the size was AA or just A, and we were able to get with let's say occasional data sends, for example, every hour, we could get it up to 5 years or even more. So yeah, maybe sometimes it's better to use a small battery, as Rolf already explained.
Yeah, and often the manufacturers of these batteries can give application notes or hints on which current is best for this type of battery. Yeah.
Okay. I believe those are all the questions. Yes.
Great.
You're welcome, everyone. Yeah, and thank you.
Also, shout out to Sujit, who is also said that he really liked the workshop. Many thanks for this nice workshop. We are glad to have you all here, and please give us some feedback about workshop. I will also contact you by email to get your feedback, because it is very important for us as well. Till next time, I wish you all the best, and thank you again, the team.
Thank you, Anita, Ruud, Rolf, Edwin, Carlo, Rock.
We are
Yes,
all here.
thank you.
Thank you.
Thumbs up
Thank
yourself.
you. Yeah. I won't mention myself.
Thank you, Tony.
Yeah. You're welcome.
Okay.
So yeah, this is all for this time from our side. And would anyone want to add anything?
Have a nice end of the week and have a nice weekend. And yeah, that's it from us. That's it from one.
Yeah, and stay in touch
Yeah.
and read the news on our sites.
Yeah.
Thank you so much. Till next time.
Bye bye.
Bye bye.